Somewhere, far beyond the reach of even our most powerful telescopes, could exist a star so dangerous that the universe itself seems to tiptoe around it. It wouldn't need to shine brightly to announce its presence. It wouldn't need to hurl massive flares in all directions or greedily swallow nearby worlds like a black hole. No, this star's weapon is something far more insidious. A magnetic field so unimaginably strong it could tear apart the very atoms that make up reality itself. And the worst part? It could do this from light years away. You wouldn't see it coming. You wouldn't feel its approach. One moment you're whole, the next, your atoms are betraying you, coming undone, their bonds shattered by an invisible, unstoppable force. This is the chilling realm of the hypermagnetar, not just a rare cosmic oddity, but a hypothetical monster that takes one of the deadliest known types of star in the universe and turns it into something so extreme, it borders on the unthinkable. Scientists have studied magnetars, neutron stars already famous for having magnetic fields trillions of times stronger than Earth's, and they've learned enough to know that even those are terrifying. But imagine taking that already unimaginable power and amplifying it by 1 trillion times. The result? A star that could sterilize whole planetary systems without moving an inch. A star that could make electronics, molecules, and even atomic nuclei unravel simply by existing in your corner of the galaxy. But before we continue, subscribe to the channel so you don't miss out on any of these videos. This isn't the type of cosmic threat that has to collide with you to kill you. It's not like a supernova whose light announces its arrival before its blast wave reaches you. The hypermagnetars reach is invisible, silent, and absolute. Your only warning might be strange, unexplained disturbances in your technology, if you were lucky enough to even notice before everything failed. If you were a planet orbiting in its kill zone, life would never have had the chance to begin. If you were a spacecraft exploring deep space, a single step too close could mean instant annihilation, systems fried, communications dead, your atoms beginning to drift apart like scattered sand. The horrifying beauty of this hypothetical star lies in how it rewrites the rules of what it means for something to be deadly. Black holes, gamma-ray bursts, rogue planets, they're terrifying in their own ways, but all have conditions, distances, and escape possibilities. The hypermagnetar doesn't chase you. It doesn't need to. Like a predator so efficient it doesn't waste energy hunting, it simply waits, an invisible sphere of death in space, erasing anything foolish enough to cross into its territory. The question is, how could such a thing even exist? Is nature capable of producing something this extreme, or would it require some unfathomable chain of cosmic events, perhaps even the hand of an alien intelligence? Could one be lurking, even now, somewhere in the Milky Way, hidden among the countless points of light we casually see in the night sky? And if it is, would we ever know before it's too late? Before we can understand this ultimate stellar predator, we first need to understand the lesser version, a star that is already one of the most dangerous objects in the known universe, the magnetar. Only then can we truly appreciate how much more nightmarish the hypermagnetar would be. A magnetar begins its life as something already extraordinary, a neutron star. Neutron stars themselves are the ultra-dense corpses left behind when a massive star explodes in a supernova. Imagine a star many times the mass of our Sun burning through its fuel, collapsing under the weight of its own gravity, and then violently blowing off its outer layers in one of the most energetic events in the universe. What's left is a core so compact that a teaspoon of its material would weigh more than 1 billion tons. The matter inside is so tightly packed that atoms no longer have room for their electrons. The nuclei are crushed together, forming a gigantic sphere of neutrons, just a few kilometers across but with a mass greater than our Sun. That's already the normal neutron star, an object so extreme it defies ordinary human experience. But sometimes, in rare cosmic circumstances, a neutron star is born spinning incredibly fast, perhaps hundreds of times per second, and with a magnetic field unlike anything else in the cosmos. These are magnetars. Their magnetic fields aren't just strong, they are mind-bendingly strong. To put it in perspective, Earth's magnetic field is about 0.5 Gauss. The most powerful laboratory magnets humans have ever built produce fields of a few tens of thousands of Gauss. A typical fridge magnet? around 100 Gauss. Now compare that to a magnetar. Its magnetic field can reach a quadrillion Gauss. That's a million billion times stronger than Earth's. This is so strong that if a magnetar were placed halfway between Earth and the Moon, its magnetic pull would be powerful enough to wipe the magnetic stripes off every credit card on the planet. Get closer, and it would do far more than mess with your electronics. It would literally distort the shapes of your atoms, tugging electrons away from their nuclei. The force is so overwhelming that the very structure of matter would begin to break down. And yet, magnetars aren't just about magnetism. Their intense magnetic fields are unstable, prone to sudden reconfigurations that release massive amounts of energy. These reconfigurations can cause starquakes on the magnetar's surface, the solid crust shifting and cracking under the strain, and these can unleash bursts of radiation so powerful they can be detected across the galaxy. In 2004, a magnetar called SGR 1806-20 emitted a flare so intense that, even from 50,000 light-years away, it briefly affected Earth's upper atmosphere and overloaded some spacecraft instruments. This was a star halfway across the Milky Way, and it still managed to touch us. Magnetars are rare. Scientists estimate there may be only a few dozen active in our entire galaxy at any given time. But their rarity is a small comfort, because their destructive range and unpredictable behavior mean they are not just a theoretical hazard. Even the base model is capable of disrupting planetary environments and killing life over large distances. If a magnetar were to wander too close to our solar system, it wouldn't need to collide with Earth to wipe us out. Its radiation and magnetic fields alone could do the job. Now, if this is what the normal version can do, already boasting the strongest magnetic fields nature has ever confirmed, imagine taking that and cranking it up by 1 trillion times. That's the hypermagnetar. It's like comparing a lightning strike to the sun going supernova. Both are dangerous, but one is on a scale so far beyond the other that the comparison almost feels unfair. If a standard magnetar is already the cosmic equivalent of an apex predator, the hypermagnetar is what happens when you turn that predator into something so overpowered it barely fits within the laws of physics as we understand them. The leap from magnetar to hypermagnetar is not just a matter of more strength. It's a transformation that pushes the very concept of magnetism into realms we've never observed, simulated, or even fully imagined. A known magnetar's magnetic field can reach around 10 superscript 1 Gauss, a figure so enormous it already defies intuition. Now multiply that by 1 trillion. A hypermagnetar would boast a field strength of 10 superscript 2 Gauss. This is a number so large it's difficult to write without scientific notation, and so powerful it would completely redefine the scale of magnetic influence in the universe. To put that in perspective, a hypermagnetar wouldn't just be the most magnetic object in existence. It would be in a category entirely of its own, so extreme that no naturally occurring object in the known universe currently rivals it. At this strength, magnetism ceases to behave like the force we're used to in everyday life. On Earth, magnets interact mostly with metals and charged particles. In the case of magnetars, the field is strong enough to affect all matter, including neutral atoms, by warping the quantum fields around them. But in a hypermagnetar, the magnetic field would be so overpowering that it could directly disrupt the strong nuclear force, the force that binds protons and neutrons together inside the atomic nucleus. This is territory beyond the extremes of any laboratory experiment, beyond the reach of particle accelerators, beyond the comfort zone of our current physics. The destructive potential here is not just worse, it's qualitatively different. If you were within its reach, you wouldn't merely be irradiated or fried by electromagnetic pulses. Your atoms would cease to be atoms. The balance of forces holding together the building blocks of matter would be so violently tipped in favor of the magnetic field that electrons would be flung away instantly, and even the nuclei themselves could be torn apart. This isn't just molecular destruction, it's elemental annihilation. And the reach, that's where it becomes truly horrifying. For a regular magnetar, the danger zone for severe atomic disruption might be measured in thousands of kilometers, still immense, but relatively localized by cosmic standards. For a hypermagnetar, the kill radius could extend for light years. entire planetary systems could lie within its influence. Worlds would be sterilized without a single meteor impact, without a single flare reaching them. Even if you were comfortably parked on a planet orbiting a stable, life-friendly star, a hypermagnetar drifting into your galactic neighborhood could silently strip your planet's atmosphere, disrupt its chemistry, and leave it a dead husk, all without ever coming close enough to be seen by the naked eye. What's perhaps most unsettling is that this isn't just an exaggerated what if for drama's sake. Theoretical physics allows for the possibility that under certain rare and extreme conditions, perhaps involving the collapse of a truly enormous star in a hypernova or an unusual cascade of magnetic amplification events, such an object could exist. It's unlikely, but the universe has a track record of creating things we thought were impossible. After all, before we discovered the first real magnetars, the idea of a neutron star with a magnetic field that strong seemed absurd too. The leap to a hypermagnetar is not just a matter of magnitudes. It's a step into a regime where the rules themselves may change. Physics as we know it is calibrated on forces that are nothing compared to this. And if one ever existed within our galaxy, its very presence could reshape regions of space on a scale that no other known object short of a supermassive black hole can match. The difference is, you can avoid falling into a black hole. You cannot outrun a magnetic field that spans light years. When we talk about magnets in everyday life, the mental picture is simple. They attract certain metals, they can pull or push on other magnets, and they can influence electric currents. Even with the most powerful magnets humans have built, the effects are still confined to these familiar interactions. But once you step into the magnetic field territory of a hypermagnetar, that everyday intuition collapses completely. At the scale of 10 superscript 2 Gauss, a magnetic field stops being a force that acts on objects, and instead becomes a sculptor of reality itself. This is because the electromagnetic force, one of the four fundamental forces of the universe, starts to overwhelm the forces that normally hold matter together. Let's break this down. Atoms, the building blocks of everything you see and touch, are held together by a delicate balance of forces. Negatively charged electrons orbit a positively charged nucleus due to the electromagnetic attraction between them. Inside the nucleus itself, the protons, which naturally repel each other because of their like charges, are held together by the strong nuclear force, the most powerful known force in nature. In normal circumstances, magnetism is far too weak to challenge these bonds. Even in the case of a normal magnetar with a magnetic field of around 10 superscript 1 Gauss, the most dramatic effects are the stripping away of electrons from atoms and the distortion of their energy states. But with a hypermagnetar, the field is so ferociously strong that it essentially rewrites the energy budget of matter. First, electrons are ripped away instantly. This isn't like ionization from heat or radiation. It's as though the space around the atom becomes so magnetically warped that the electrons have no stable orbit left. The field forces them into elongated, needle-like paths aligned along magnetic field lines. Quantum mechanically, their allowed energy states are completely altered, causing the atoms themselves to stretch like cosmic spaghetti. That alone would be enough to obliterate normal matter, but the hypermagnetar doesn't stop there. At this scale, the magnetic pressure, yes, magnetism can exert pressure, can rival or even exceed the forces binding protons and neutrons inside the nucleus. This means the strong nuclear force, which normally reigns supreme inside atomic nuclei, is suddenly in a losing battle. Protons and neutrons could be torn apart or rearranged, potentially breaking matter down into a soup of subatomic particles. Imagine holding a snowflake in your hand and watching it dissolve into mist without any heat, melting, or chemical reaction, just gone, because the invisible conditions around it no longer allow it to exist as it once did. Now replace the snowflake with the most durable, indestructible object you can think of, steel, diamond, tungsten, and the same principle applies. The hypermagnetar's field doesn't care about hardness, strength, or temperature. It erases the very definition of solid, by dismantling matter's structure at its most fundamental level. The terrifying part? These effects are not confined to a small, touch zone, like the surface of the star. In a hypermagnetar, The field's reach would be measured in astronomical units, potentially in light years. The electromagnetic field lines extend outward from the star in every direction, warping the vacuum of space itself. In physics, the vacuum isn't truly empty, it seethes with quantum fluctuations, and at these field strengths, even the virtual particles popping in and out of existence could be distorted, possibly creating exotic states of matter never seen in nature. For anything caught in this magnetic maelstrom, there's no safe configuration. Molecules are shredded as their chemical bonds, normally mediated by shared electrons, fail instantly. Complex structures like proteins, DNA, and even the crystalline lattices of metals become meaningless as the field dictates entirely new arrangements of charged particles. If a living being somehow drifted into the edge of this zone, death would be instantaneous, not from radiation or impact, but because their very body would no longer be made of intact atoms. It's destruction at a level more intimate and final than almost any other known force can achieve. And here's an even more unsettling layer. Such a magnetic field would also twist the paths of photons, the particles of light. In ordinary space, photons travel in straight lines unless deflected by gravity, as in gravitational lensing. But in an ultra-strong magnetic field, light itself interacts differently with the vacuum, a phenomenon called vacuum birefringence. This means the hypermagnetar could quite literally distort the way light behaves around it, not by warping spacetime like a black hole, but by warping the very electromagnetic rules light follows. In effect, reality near the star would be running on a different physical operating system. So, when we say a hypermagnetar's magnetic fields could shred reality, it's not just poetic exaggeration. At the atomic and subatomic level, the star's influence would rewrite the possible configurations of matter and energy. This isn't magnetism as we know it, it's magnetism as a universal sculptor, taking apart and reshaping the universe's building blocks without so much as lifting a tangible finger. If such an object existed within even a few dozen light years of Earth, we wouldn't just be talking about the end of life here. We'd be talking about the disassembly of the solar system itself into a fog of dissociated particles. Planets wouldn't collide or burn, they'd simply stop being planets. And yet, we've only scratched the surface of what such a field would mean for its surroundings. To truly appreciate the scale of this destruction, we have to look at just how far its influence would reach, not just in meters or kilometers, but in light years. That's where the next part takes us. The atomic destruction zone surrounding a hypermagnetar is a cosmic expanse of unimaginable devastation, where the fundamental fabric of matter is undone over distances so vast they boggle the mind. This kill radius is not measured in kilometers or even astronomical units, but in light years, distances spanning trillions of kilometers, stretching across multiple star systems, dissolving worlds without a trace. To understand the scale and nature of this annihilation, we must first revisit what holds matter together, and then explore how the hypermagnetar's magnetic field overpowers those forces on an unprecedented scale. At its core, matter consists of atoms, tiny structures where negatively charged electrons orbit positively charged nuclei. The electromagnetic force is what binds these electrons to nuclei, keeping the atom intact. Within the nucleus, an even stronger force, aptly named the strong nuclear force, holds protons and neutrons tightly together despite the repulsive electromagnetic forces between positively charged protons. This delicate balance allows atoms, molecules, and by extension, all matter to exist as stable entities. Under normal astrophysical conditions, including the environments around ordinary stars or even neutron stars, atoms can be ionized, stripped of electrons, but the nuclei themselves remain largely intact. This is a key distinction. Ionization affects the electron cloud, but nuclear forces keep the core stable. However, a hypermagnetar's magnetic field redefines these boundaries. With field strengths approaching 10 to the power of 27 Gauss, trillions of times stronger than the most intense magnetars known, this magnetic field doesn't simply strip electrons away. It destroys the very structure of the atom. Electrons, once bound to their nuclei, are no longer confined by electromagnetic attraction. Instead, they are pulled into elongated, needle-like orbits aligned strictly along magnetic field lines, as dictated by quantum mechanics under extreme magnetic fields. This distorts the shape of atoms themselves, stretching them into unnatural forms that no longer behave like stable matter. The field's influence penetrates even deeper. Once the electrons are stripped and distorted, the hypermagnetar's magnetic pressure begins to compete with the strong nuclear force inside atomic nuclei. Ordinarily, the strong nuclear force reigns supreme within the nucleus, overcoming electromagnetic repulsion between protons. But the magnetic pressure here is so extreme that it can overwhelm this nuclear cohesion. The protons and neutrons inside nuclei are forced apart, causing nuclei to disintegrate into their constituent subatomic particles, quarks, gluons, and other exotic particles. This is not mere ionization or molecular dissociation, it is the complete deconstruction of matter at the nuclear and subnuclear levels. What does this mean for the scale of destruction? The kill radius around the hypermagnetar would be enormous, extending for multiple light years. This vast region, a sphere centered on the star, represents a zone where normal matter cannot survive in any recognizable form. Any solid object, planets, moons, asteroids, comets, that drifts into this zone would be disassembled atom by atom, molecule by molecule, into a diffuse cloud of elementary particles. The familiar solidity of matter gives way to a plasma-like state composed of free protons, neutrons, electrons, and other particles caught in a relentless magnetic maelstrom. From a distance, this region might seem eerily calm, devoid of the brilliant flares or explosive signatures that characterize many cosmic catastrophes. Instead, the destruction is silent and invisible, no collision debris, no shockwaves, just a slow but absolute erasure of matter structure. Photons traveling through this region would experience extreme polarization and vacuum birefringence, phenomena where the vacuum of space itself behaves like a prism, twisting and splitting light in unusual ways. The zone would warp electromagnetic waves, scattering and distorting signals from distant stars and galaxies, potentially offering clues to astronomers hunting for these elusive beasts. The spatial scale of this atomic destruction is so vast that it can encompass entire star systems comfortably within its radius. For context, the nearest star to our Sun, Proxima Centauri, lies about 4.24 light-years away. Imagine a sphere of magnetic destruction with a radius several times this distance, an invisible death zone swallowing not just planets orbiting a doomed star but neighboring stars and their planetary retinues as well. Entire regions of the galaxy could become sterilized, rendered utterly inhospitable to life by the silent, insidious reach of this magnetic behemoth. Within this radius, even the atmospheres of stars could be stripped away. Stellar atmospheres, composed mostly of ionized gases, would be vulnerable to the immense magnetic shear forces. The hypermagnetar's field would distort and pull on the charged particles in these outer layers, potentially destabilizing the star's surface and disrupting fusion processes. Nearby stars might become gravitationally and magnetically perturbed, leading to chaotic orbits of their planets, or even triggering premature stellar deaths. The implications for any form of life are devastating. Life, as we understand it, depends on complex molecules, proteins, nucleic acids, carbohydrates, built from atoms arranged in very specific ways. The hypermagnetar's field doesn't just break chemical bonds, it destroys the fundamental atomic scaffolding necessary for these molecules to exist. Any biosphere within this kill radius would be annihilated instantaneously, not by heat or radiation alone, but by the collapse of the physical matter composing living organisms. This would occur long before any electromagnetic radiation or explosive event could reach them, rendering the zone effectively sterile. The consequences extend even further. Dust grains, the seeds of planet formation, would be pulverized into elementary particles. Molecular clouds, those vast nurseries where stars and planets form, could be disrupted or prevented from coalescing under the magnetic tyranny of a hypermagnetar. The star could act as a cosmic desert, carving out empty voids within galaxies where matter itself refuses to settle or persist. Yet, this zone remains completely invisible to the naked eye. The magnetic field itself cannot be seen, it is detected only by its effects on charged particles, radiation, and space-time itself. To an observer, the region might appear as an unremarkable patch of space until powerful telescopes detect anomalous gamma-ray bursts, unusual polarization patterns, or distortions in starlight passing nearby. The silent devastation within could continue unchecked, growing larger as the hypermagnetars' influence reaches farther, swallowing systems without a single dramatic explosion to announce its presence. In essence, the kill radius of a hypermagnetar is a cosmic no-go zone where the familiar building blocks of the universe are utterly undone. Its boundaries are not marked by light or heat but by the absence of stable matter itself, a vast and silent empire of destruction stretching across the cosmos. Within this sphere, existence as we know it is impossible, and the universe becomes a place of raw, unrecognizable chaos dominated by the most extreme magnetism ever conceived. The reach of a hypermagnetar is nothing short of cosmic horror writ large. Its influence spans not just the immediate vicinity but extends across light years of space, a zone so vast that entire star systems could be sterilized without the star ever moving an inch closer. This is not an active hunter chasing down prey, nor a star unleashing fiery explosions that travel through space over time. Instead, it is a silent, static tyrant whose magnetic dominion extends like invisible fingers reaching out and tearing apart matter across astronomical distances. The effect is both subtle and devastating, a slow but absolute sterilization that unfolds over unimaginable scales. To truly appreciate the magnitude of this threat, one must consider how typical stellar influences operate. Most stars affect their immediate neighborhoods through gravitational pull, radiation, solar winds, and occasional explosive outbursts like supernovae or gamma-ray bursts. Even the most violent events are often transient, localized, or directional. In contrast, a hypermagnetar's magnetic field would envelop a vast sphere of influence, bathing all matter within in a constant, unrelenting electromagnetic fury. This is a force that permeates the vacuum itself, bending, breaking, and ultimately erasing the atomic structure of everything caught within its radius. Imagine a star system like our own solar system, composed of a central sun surrounded by planets, moons, asteroids, and comets. Placed within the expansive magnetic field of a hypermagnetar, the solar system's delicate balance would collapse. The magnetic field would tear apart planetary atmospheres, stripping away gases and ionizing matter at a fundamental level. Oceans would be broken down into constituent particles, their molecules ripped apart before they could even vaporize. Rocky planets and moons would crumble, not through impact or heat, but through the disassembly of their atomic bonds. What makes this form of destruction so chilling is its reach. The magnetic field's kill radius could extend many light years, distances that dwarf the size of even large star systems. This means multiple systems could be caught within this sphere of annihilation simultaneously. Planets orbiting distant suns could be sterilized without warning, their surfaces dissolved atom by atom as the invisible magnetic maelstrom tears their molecules asunder. Life, if present, would be obliterated in an instant, even before any other signs of cosmic catastrophe appeared. Moreover, this annihilation requires no direct contact or explosive collision. The hypermagnetar can remain fixed in space while its magnetic influence extends outward, indifferent to distance within its kill radius. Unlike gamma-ray bursts or supernova shockwaves that lose intensity over distance, the static magnetic field remains potent, an ever-present hazard that sterilizes all within reach. It is a zone where the laws of physics enforce an absolute boundary on the existence of matter, redefining the concept of a safe distance in space. The implications for galactic ecology are profound. A hypermagnetar existing within a galaxy could carve out vast sterile voids, regions where star and planet formation is suppressed. Life cannot gain a foothold, and matter is perpetually broken down at the atomic level. These barren expanses would appear as cosmic deserts amid the lush stellar nurseries elsewhere in the galaxy, invisible in visible light but betraying their presence through subtle distortions in electromagnetic observations. For any intelligent civilization, the approach of such a star would be a slow, inescapable doom. Because the kill radius spans light years, warning signs might arrive long before the star itself does, manifesting as strange bursts of gamma radiation, peculiar magnetic distortions, or unexplained disappearances of celestial bodies. Yet, by the time these signs are recognized and understood, escape would be nearly impossible. The scale and intensity of the magnetic field leave no room for evasive maneuvers or technological shields capable of protecting entire planets. This vast zone of death extends beyond the boundaries of human comprehension, not just in terms of physical scale, but in the nature of destruction itself. It is a silent predator that kills without a trace, erasing entire star systems with no explosions, no shockwaves, and no cries of agony. The hypermagnetar's magnetic field is an omnipresent executioner, a cosmic janitor sweeping clean swaths of the universe, leaving behind only empty space and the faint echoes of its presence in distorted light. In this way, the hypermagnetar challenges our notions of cosmic violence and danger. It is not merely a star-gone supernova or a black hole's voracious maw. It is a new kind of threat, one that sterilizes and dissolves the universe's building blocks across vast distances. While gravity governs the dance of planets and stars, here magnetism claims dominion, reshaping entire regions of space into lifeless voids without a single physical encounter. If such a star lurks in our galactic neighborhood, its silent, far-reaching hand could already be at work, sterilizing worlds long before humanity even notices the threat. The universe might harbor many such monsters, invisible to our eyes, their kill zones spreading silently through the dark, waiting for the next unlucky system to drift too close. It is a cosmic terror of the highest order, not because it screams or explodes, but because it annihilates with an unyielding, all-encompassing grip that stretches across the light years. In the presence of a hypermagnetar's magnetic field, the familiar structure of matter begins to unravel in the most literal sense. Under normal circumstances, atoms maintain their stability because electrons are bound to their nuclei by electromagnetic forces. The positive charge of the protons pulls the negatively charged electrons into well-defined orbits, creating the chemical building blocks of everything from hydrogen gas clouds to human bodies. But near a hypermagnetar, that relationship is violently severed. Its magnetic field isn't merely strong enough to pull a compass needle from miles away. It's so incomprehensibly powerful that it directly manipulates the very quantum states of electrons. In such an environment, the magnetic energy in a region of space can exceed the binding energy holding electrons in place. When this threshold is crossed, electrons are forced into elongated paths aligned with the magnetic field lines. They are ripped out of their orbits, hurled away at near-light speeds, and no amount of normal atomic force can bring them back. The result is an environment where chemistry, as we know it, ceases to exist. Without electrons, atoms can't form molecules. Carbon can't bond into organic chains. Oxygen can't pair into breathable air. Water can't be more than two separate types of ions drifting apart. The very possibility of life-supporting structures collapses instantly. These stripped electrons, now freed from their atomic homes, don't simply wander aimlessly. They spiral along the hypermagnetar's field lines, emitting radiation as they go. This radiation bathes the surrounding space in deadly high-energy photons, compounding the destruction with an invisible storm that can penetrate deep into planetary crusts. But it doesn't stop there. Once electrons are gone, the bare atomic nuclei remain, now positively charged and desperately unstable in the absence of their electron cloud. These nuclei are also assaulted by the relentless magnetic field, which can stretch them physically out of shape. The forces at work here are strong enough to deform the nuclei themselves, a process called nuclear deformation, where the once roughly spherical clusters of protons and neutrons are twisted into elongated or flattened configurations. If the stress is great enough, the nuclei can disintegrate entirely, breaking down into smaller particles like protons, neutrons, or even more exotic fragments. This means that not only is chemistry impossible within this ripping zone, but even the fundamental architecture of matter itself is under siege. For a planet or a star system caught in this field's influence, the destruction wouldn't look like a traditional explosion. There would be no visible fireball, no dramatic shockwave. Instead, matter would simply begin to dissolve at the subatomic level. Rocks would not shatter, they would evaporate into charged particles. Atmospheres would vanish without so much as a whisper, their atoms undone before they could be pushed away by solar winds. Even the metallic cores of planets, typically resistant to most forms of external stress, would disassemble atom by atom, their electrons torn away long before the physical structure could resist. The sheer scale of this process is staggering. Within light years of a hypermagnetar, every atom is at risk of this dismemberment. For a moment, imagine a habitable planet orbiting a distant star. The people on its surface might first notice something odd: electronics behaving erratically, communication systems breaking down, navigation becoming impossible as compasses spin uselessly. But this would only be the beginning. As the field strength rises beyond their tolerance, the very atoms in their bodies would start to lose electrons. Blood chemistry would change in an instant. Cell membranes would destabilize. Within seconds, life would be reduced to scattered subatomic debris. It's an execution method written by the cosmos itself, silent, instant, and inescapable. Even free-floating dust in interstellar space is not safe. The hypermagnetar's reach doesn't discriminate between a living world and a lonely asteroid. Microscopic grains of carbon drifting between stars can be stripped bare, left as inert atomic cores drifting further into the void. Over millions of years, the field could sweep clean entire regions of space, sterilizing everything within its magnetic horizon. If such an object existed near our own galactic neighborhood, it would act as a kind of cosmic eraser, removing all traces of matter's complexity, and leaving only a barren fog of unbound particles. And here's the most chilling part: the electrons torn from their nuclei don't simply vanish. In their frenzied escape, they generate intense bursts of synchrotron radiation, light and energy produced by particles spiraling at relativistic speeds along magnetic field lines. These bursts could be powerful enough to disrupt or even destroy the delicate balance of atmospheres many light years away, making them an additional hazard on top of the already unimaginable disassembly of atoms. This means that the hypermagnetar's deadliness isn't just local. Its effects can cascade outward, triggering chain reactions of destruction in worlds far beyond its immediate kill zone. In a way, the hypermagnetar turns the very rules of atomic stability against themselves. It doesn't need to smash atoms together like a supernova, nor tear space itself like a black hole. It simply reshapes the environment until the fundamental forces holding matter together are overridden. At that point, matter doesn't explode, it unravels. A place once rich with planets, moons, and stars becomes a quiet graveyard of stripped, drifting particles, all of them robbed of their electrons, their chemistry, and their history. Unlike the chaotic violence of an asteroid impact or the engulfing pull of a black hole, this monster of the cosmos kills without even touching you. It doesn't need to smash into planets, hurl radiation like a gamma-ray burst, or drag entire star systems into its maw. Instead, it simply sits in space, quietly radiating death across distances so vast they defy human comprehension. Its magnetic field alone is the executioner, an invisible, omnipresent force that seeps through everything in its reach. You could be orbiting a completely different star, light years away, and still fall victim to it without ever seeing it in your sky. The moment you drift within its sphere of influence, the laws of physics themselves turn against you. Atoms, the building blocks of every star, planet, and living being, lose their integrity. The electrons are ripped away first, torn loose by the irresistible pull of the magnetic field, leaving bare, unstable nuclei behind. These nuclei, stripped of their protective electron clouds, are then forced apart, their bonds shattered by relentless magnetic pressure. For entire worlds, this process is instant and total. Oceans would vaporize without boiling, rock and metal would dissolve at the subatomic level, and the very structure of matter would collapse into an unrecognizable haze of free particles. It's not destruction in the way we typically imagine. There are no flames, no explosions, no visible wave of fire sweeping across the surface. Instead, it's a quiet, surgical unmaking of reality itself, the erasure of existence at its most fundamental scale. Planets caught in its reach wouldn't even have time to crumble. One moment they'd be whole, orbiting peacefully around their suns. The next, they'd be a diffuse, invisible fog of raw particles scattered into the void. This is why it's more terrifying than any supernova or asteroid. You can't see it coming, and even if you could, there's nothing to outrun. The kill zone moves with it, but it doesn't have to move at all to erase everything nearby. Even if it were completely motionless in space, its lethal influence could sterilize multiple star systems over millennia, simply by existing. Civilizations could vanish without a clue, their worlds wiped clean without a single trace of what happened, as if they had been deleted from the universe's memory. No sound, no light, no warning, just the silent rewriting of reality itself. The strangest part is that from a great distance, it might look harmless. It wouldn't necessarily shine brighter than other stars or pulse violently like a supernova remnant. You could be looking directly at it through a telescope, admire its strange glow, and never realize that if you moved just a fraction of a light year closer, you'd be walking into an execution chamber built by nature. This is a predator that doesn't hunt, it waits, confident in the sheer size of its invisible reach. And unlike other cosmic killers that burn out quickly after their violent birth, this one could remain active for thousands, maybe millions, of years. It could be drifting somewhere in our galaxy right now, passing through regions filled with unsuspecting planets. It doesn't need to aim, it doesn't need to fire, its very presence rewrites the atomic rules that keep matter together. If death ever had a perfect form in the cosmos, this would be it, one that kills without touching, without moving, without warning, and without mercy. Imagine, for a moment, the hypermagnetar not as a distant point of light in the cold abyss, but as a sleeping predator with the power to lash out without warning. Every so often, this monstrous star releases a tantrum of pure energy, an eruption of electromagnetic fury so intense that it defies the human imagination. These are not the gentle, steady streams of light we receive from the sun. No, these are violent, short-lived outbursts, gamma-ray flares that are so concentrated in energy, they could, in a fraction of a second, unleash more power than our sun produces in hundreds of thousands of years. To call them deadly would be an understatement. These bursts are cosmic sledgehammers, and the hypermagnetar wields them with terrifying precision. When such a flare erupts, it does not politely stay confined to the neighborhood of the star. It doesn't need to. The energy release travels across the galaxy at the speed of light, cutting through the vacuum like invisible tidal waves of annihilation. There is no sound, no warning, no shimmering light in the sky for an unsuspecting world to see coming, only an onslaught of high-energy gamma photons capable of dismantling molecular bonds and stripping atmospheres bare. If a planet lies in the path of one of these bursts, distance offers only partial protection. Even from thousands of light-years away, the incoming gamma-ray surge could still fry the ozone layer of an Earth-like world, leaving it naked to the lethal ultraviolet glare of its parent star. Life, even if thriving moments before, could be reduced to extinction-level silence almost instantly. These gamma-ray flares are born from the unimaginable stresses within the hypermagnetar's magnetic field, a field so intense, it twists and cracks the star's crust, triggering starquakes that release titanic amounts of energy. In those moments, the outer layers of the star become like the snapping cables of a cosmic suspension bridge, recoiling violently and discharging energy in all directions. The radiation is so compacted, so energetic, that it not only threatens living organisms but can also disrupt the very structure of matter itself. Electrons are ripped from their orbits, atoms are ionized into chaos, and complex molecules disintegrate in an instant. For civilizations, advanced or otherwise, caught in the blast path, survival is not a matter of building stronger shields or hiding underground. This is not a storm you can bunker through. The radiation penetrates shielding, overwhelms electronics, and blinds detection systems in a wave of static. Communication networks would collapse. Spacecraft hulls would sizzle with energy, and their onboard systems would fry from radiation overload before anyone had time to process what was happening. Astronomers often speak of habitable zones around stars, where liquid water and life might flourish. The hypermagnetar, however, carves out something far more terrifying, an uninhabitable sphere, an invisible boundary extending across light-years where its bursts render entire sectors of the galaxy sterile. The sheer unpredictability of these gamma-ray flares makes them even more sinister. Unlike a supernova, which announces its arrival with observable signs, these magnetic monsters can lash out seemingly at random. One moment, they appear as relatively calm, though still immensely dangerous, stars. The next, they unleash beams of radiation so sharp and concentrated they can outshine the rest of the galaxy for a few brief seconds. It's in those moments that the hypermagnetar becomes the galaxy's executioner, its power radiating across the cosmos in a silent but unstoppable wave. And these are not rare events. While most stars spend billions of years in predictable, stable phases, magnetars, and by extension, our hypothetical hypermagnetar, are notoriously volatile. In its hyperpowered state, even the smallest fracture in its magnetic equilibrium could release a flare strong enough to affect not just nearby systems, but worlds many star systems away. For a galaxy that spans over 100,000 light-years, this means a single hypermagnetar could, over its violent lifetime, repeatedly send lethal pulses into regions far beyond its immediate vicinity, overlapping with zones already damaged by previous bursts. The effect is cumulative. Planets hit multiple times might never recover biologically, their atmospheres permanently eroded, their oceans evaporated, and their surfaces bathed in unending radiation. To grasp the scope of such destruction, imagine a single burst emanating from a point thousands of light-years away, reaching out and sweeping across space like an invisible tsunami. That wave doesn't just pass through empty void, it intersects with stars, planets, moons, and potentially habitable systems. And unlike a physical tsunami, which crashes and retreats, this wave is the radiation equivalent of a searing brand pressed against the flesh of the galaxy. Instantaneous damage, permanent scars. Even dead, rocky worlds without atmospheres wouldn't escape untouched. Their surfaces would be altered, baked, and chemically transformed, their crust infused with the signatures of the hypermagnetar's wrath. What makes these waves of electromagnetic fury truly terrifying is that they erase distance as a defense. In most cosmic encounters, safety comes from being far away. The further you are from a black hole, a supernova, or a gamma-ray burst, the less danger you're in. But here, the rules bend. The hypermagnetar's flares are so energetically rich, they don't need proximity to devastate. Even at astronomical distances, the radiation density remains high enough to cause chaos, much like a sniper who can hit a target from beyond the range of sight. Space, for all its vastness, suddenly feels claustrophobic when a single object can project lethal influence across such a staggering range. There's also the chilling possibility that such a flare could intersect with the trajectory of a developing civilization's homeworld, wiping it out before it even begins to understand the nature of its enemy. Perhaps somewhere, deep in the history of the galaxy, entire branches of life's evolutionary tree have been pruned by the hypermagnetar's tantrums. Civilizations that might have flourished never made it past their earliest stages, their skies briefly lit by a deadly pulse from an unseen star, followed by centuries of silence. In that sense, the hypermagnetar is not merely a danger to individuals or planets, it's an obstacle to the very concept of life's persistence in the cosmos. The waves it sends are merciless. They don't discriminate between barren rock and lush paradise, between the homeworld of an emerging interstellar culture and a lonely moon circling a cold gas giant. They strike with the same efficiency, the same brutality, across any target unfortunate enough to be aligned with their path. And unlike other stellar threats, there is no negotiation, no possibility of deflection, no safe distance within its immense sphere of influence. It is, in every sense, a weaponized piece of nature, a star so charged with energy that space itself becomes the battlefield, and every point within range is a potential casualty. The hypermagnetar's waves of electromagnetic fury remind us of a truth about the universe that is easy to forget when we gaze at its beauty from afar. Space is not passive. It is not merely a stage for the slow ballet of planets and stars. It is a battlefield in which energy and matter clash on scales so immense, they render human concepts of danger almost meaningless. And somewhere, perhaps closer than we'd like to imagine, a hypermagnetar could be waiting, quiet for now, but ready at any moment to unleash another invisible tsunami of annihilation across the galaxy. Imagine, without warning, the familiar night sky above Earth begins to change. The stars we've known for millennia flicker with an unnatural shimmer, and an eerie glow suffuses the atmosphere. Invisible to our eyes, waves of lethal radiation cascade over the planet, infiltrating every layer of the atmosphere, permeating the ground beneath our feet, and reaching deep into the oceans. This is no ordinary cosmic event. This is the harbinger of annihilation from a hypermagnetar's relentless electromagnetic fury. As the radiation intensifies, the Earth's protective magnetic field, our planet's shield against solar and cosmic radiation, struggles to withstand the onslaught. Normally, the magnetosphere deflects harmful particles, but the magnetic intensity emitted by a hypermagnetar can overwhelm this defense. Particles from the star's gamma-ray bursts and high-energy electromagnetic waves penetrate deeper and deeper, tearing at the molecular fabric of our atmosphere. The ozone layer, which blocks the sun's most harmful ultraviolet radiation, begins to rapidly deteriorate, allowing deadly UV rays to scorch the surface below. The immediate effects on our technology are catastrophic. Satellites in orbit begin to fail, their delicate electronic circuits fried by the intense radiation. Communications black out, GPS navigation becomes erratic, and the Internet, a backbone of modern civilization, collapses under the strain. Power grids falter as transformers and power lines surge beyond capacity, triggering widespread blackouts. Planes lose contact with control towers, compasses spin erratically, and ships lose navigational guidance. Humanity's technological marvels, which allow us to explore and connect across the globe, become useless relics overnight. But the technological failure is just the beginning. The skies themselves take on a haunting glow, lit not by the familiar stars but by charged particles interacting with Earth's atmosphere. Similar to the aurora seen near the poles, but vastly more intense and widespread, the atmosphere crackles with electric discharges that light the heavens in eerie hues of green, purple, and red. This celestial light show, though beautiful, signals a world under siege. The very air seems charged with a restless energy, and storms of electrical activity rage uncontrollably across the planet. As the radiation penetrates to the surface, it begins to ravage life itself. The gamma rays and high-energy particles break molecular bonds in DNA, causing massive mutations and cellular death. Plants wither and die, unable to photosynthesize properly as their cellular structures collapse. Animals suffer from radiation poisoning, their nervous systems fried by invisible energy waves. Human beings face an invisible enemy that attacks from within, destroying cells, impairing immune systems, and causing fatal illnesses. Even the microorganisms that form the base of the food chain are wiped out, disrupting entire ecosystems in an instant. This chain reaction triggers a planetary collapse. Food sources vanish as crops fail and animal populations plummet. Oceans, stripped of their plankton and marine life, become vast dead zones. Forests burn not from fire, but from the decay and collapse of life processes on a molecular scale. The air, once vibrant with the sounds of birds and insects, falls silent. Within months, or even weeks in some regions, life as we know it is extinguished. The radiation also disrupts weather patterns on a global scale. The delicate balance of heat and moisture, once governed by the sun and Earth's atmosphere, is thrown into chaos. Hurricanes and typhoons grow in size and intensity, powered by unstable atmospheric energy. Prolonged droughts parch large swaths of the continents, while other regions drown under relentless, radiation-driven storms. The planet's climate spirals into disorder, compounding the catastrophe wrought by the hypermagnetar's invisible hand. Even the oceans are not spared. Charged particles penetrate water, breaking apart molecules and altering the chemical balance. Acidification accelerates, coral reefs bleach and die, and marine life suffocates in expanding dead zones. The collapse of marine ecosystems reverberates through the entire biosphere, severing the food chains that once sustained life on land and sea alike. At night, the skies continue to glow with unnatural colors, as the hypermagnetar's influence floods Earth's atmosphere with ionized particles. The familiar constellations vanish behind a spectral haze of light, turning the night into a surreal and unsettling spectacle. This glow is both a warning and a lament, a final farewell from a world caught in the grip of a cosmic predator. In this apocalyptic scenario, the hypermagnetar's silent, invisible power becomes terrifyingly tangible. It is a force that requires no impact, no explosion, no collision to wipe out life. Instead, it operates through a slow but absolute erasure of the molecular and atomic bonds that make life possible. The world doesn't explode, it unravels, atom by atom, cell by cell, until all that remains is a dead, glowing husk. Such a catastrophe would not just mark the end of human civilization but would represent a fundamental rewriting of Earth's natural order. It would be a stark reminder that the universe is filled with forces far beyond our control, forces that could snuff out life with the quiet efficiency of a predator waiting patiently in the dark. This vision of Earth bathed in radiation and stripped of life serves as a chilling testament to the hypermagnetar's terrifying power. It's a nightmare scenario, but one grounded in the relentless logic of physics taken to extremes. And while no hypermagnetar is currently known to threaten our planet, the possibility lingers in the shadows of the cosmos, a silent, invisible menace that turns the sky into a deadly weapon, and the universe itself into a graveyard. Picture a spacecraft hurtling through the void of space, its onboard systems finely tuned to navigate the darkness with precision. It carries explorers, scientists, or perhaps a colonization mission destined for a distant star system. All its instruments, navigation arrays, communication systems, life support controls, depend on delicate electronics and finely balanced magnetic components. Now imagine this vessel suddenly crossing into the invisible yet deadly reach of a hypermagnetar's magnetic field, where the rules of reality are distorted beyond recognition. Instantly, the spacecraft's systems begin to falter. The hypermagnetar's magnetic field is not just strong, it is unimaginably powerful, dwarfing any magnetic environment previously encountered. As the ship enters this lethal zone, the magnetic flux bombards the ship's circuits with intense electromagnetic interference. The carefully shielded processors, designed to withstand cosmic radiation and solar storms, are overwhelmed within seconds. Microchips fry as currents surge uncontrollably, data buses spark and burn, and power supplies collapse. Navigation computers lose their ability to process inputs, the autopilot fails, and the ship becomes an unresponsive hulk drifting aimlessly in space. Even the physical hardware is vulnerable. Magnetic fields of this magnitude induce currents in metal components, warping delicate instruments and twisting wires. Sensors measuring position, speed, and orientation become useless as the magnetic interference distorts their signals. Gyroscopes and magnetometers, the very tools used for spatial awareness, are rendered unreliable or completely inoperative. The star trackers that lock onto distant suns for navigation lose sight as the local magnetic storm blinds their sensors. Communication is severed next. Radio waves, the lifeline of any spacecraft, cannot penetrate the thick electromagnetic haze created by the hypermagnetar. Signals are scrambled, delayed, or absorbed entirely. Any attempt to send distress calls back to mission control is swallowed by the chaos, leaving the crew isolated and unaware of their impending doom until systems go dark. Life support systems, reliant on electronically controlled valves and environmental monitors, falter as sensors fail to read critical data accurately. Oxygen levels, temperature controls, and carbon dioxide scrubbers malfunction, putting the crew at immediate risk. Automated safety systems designed to compensate for hardware failures are overwhelmed by the sheer magnitude of the electromagnetic assault, rendering manual overrides impossible. Even shielding technology, the latest in radiation protection, cannot counteract the combined effects of the magnetic field and the bursts of high-energy radiation flooding the area. Electronics built for resilience against solar flares and cosmic rays are powerless against this hypermagnetar's fury. The magnetic field alters the quantum states of electrons within semiconductor materials, causing sudden and irreversible damage to transistors and logic gates. In essence, the spacecraft's brain is electrocuted before any physical damage occurs. For unmanned probes or satellites, the story is no less dire. Instruments designed for long-term scientific study are rendered useless, their sensors blinded or destroyed within moments. Data stored on onboard memory chips is corrupted or lost entirely. The spacecraft becomes a lifeless shell, drifting silently through the hypermagnetar's domain, its mission cut short by a force that no amount of engineering could prepare for. This instantaneous shutdown is not merely a technical failure but a death sentence for the crew aboard. Without navigation, the ship is at the mercy of gravitational fields, potentially pulled towards the hypermagnetar or into nearby celestial bodies. Without communications, rescue is impossible. Without life support, survival time dwindles rapidly. The vastness of space offers no sanctuary. The once reliable environment of interstellar travel becomes a minefield of electromagnetic chaos. The hypermagnetar's invisible yet impenetrable barrier around itself thus acts as both shield and executioner. It prevents any approach, not through force of collision or heat, but by neutralizing the technology that allows spacefaring civilizations to explore and survive. Any spacecraft venturing into this zone is effectively blind, deaf, and powerless, reduced to drifting debris subject to the star's overwhelming magnetic and gravitational influence. This phenomenon also presents a terrifying challenge for future space exploration. Even if humanity or other intelligent species develop technologies capable of traveling vast interstellar distances, the presence of a hypermagnetar in a region of space could act as a deadly no-go zone, a magnetic minefield beyond which no probe or ship can pass without instant destruction of its systems. In the grand cosmic scheme, this silent disabling of spacecraft is yet another facet of the hypermagnetar's immense lethality. It doesn't need to physically destroy with explosions or gravity wells alone. By cutting off the technological lifelines of exploration and survival, it enforces its reign through technological suffocation. To approach it is to court certain doom, not just from the environment, but from the very tools meant to protect and navigate that environment. As humanity's reach extends into the stars, the specter of the hypermagnetar looms large, not just as a celestial curiosity, but as a sobering reminder that some forces in the universe are too powerful, too absolute, for any technology to overcome. For now, we observe from a safe distance, but the question remains, should we ever encounter such a star, how will we survive when our ships are turned into silent tombs by the unseen hand of magnetism? The idea of a hypermagnetar, a star with a magnetic field 1 trillion times stronger than any known magnetar, presents a profound puzzle that pushes the boundaries of our understanding of physics. From the moment we imagine such a colossal magnetic field, fundamental questions arise. How can such a field exist? How is it generated? And most perplexingly, how does the star itself survive under the weight of this impossible magnet? At the core of the problem lies the intimate connection between magnetic fields and matter. Magnetic fields arise from moving electric charges, currents within the star's incredibly dense interior. In neutron stars, these currents flow within exotic states of matter packed so tightly that a teaspoonful would weigh billions of tons. The known magnetars possess magnetic fields on the order of 10 to the power of 15 Gauss, already so extreme that their effects stretch beyond conventional physics. But a hypermagnetar, boasting a magnetic field 1 trillion times stronger, reaching into the realms of 10 to the power of 27 Gauss or more, would confront the star with forces almost inconceivable. One of the first challenges is the magnetic pressure. Magnetic fields exert pressure outward, pushing against the star's matter. In normal stars, thermal pressure and radiation pressure balance gravity's inward pull, keeping the star stable. In neutron stars, the quantum degeneracy pressure of neutrons resists collapse. But in a hypermagnetar, the magnetic pressure alone would surpass the ability of the star's matter to contain it. The magnetic field lines would press outward so forcefully that, in theory, they could tear the star apart from the inside out, blowing the star apart like a cosmic bomb. This leads to a paradox. To create such an immense field, the star must have an enormous amount of internal currents, but those currents would destabilize the very structure that sustains the star. The star would need to simultaneously support and contain this magnetic monster without being torn apart. Existing models of neutron star physics simply cannot reconcile this. The star would have to be in an exotic state, where matter behaves in ways not yet fully understood, perhaps a new phase of nuclear matter or some form of exotic quark gluon plasma stabilized by forces beyond our current theories. Then there's the question of energy. Generating and sustaining such a magnetic field requires vast amounts of energy. Even magnetars, whose fields are the most powerful known, derive their magnetism from a combination of rapid rotation and the leftover heat from their formation. But to reach hypermagnetar levels, the star would need a nearly unimaginable reservoir of energy, and an incredibly efficient mechanism to convert that energy into magnetic fields. Perhaps, as some theorists speculate, a hypernova, a supermassive star's explosive death, could compress energy so intensely that these magnetic fields emerge, but even then, maintaining them over time challenges the limits of what physics can explain. The star's rotation also factors into this enigma. Rapid spinning can amplify magnetic fields through a dynamo effect, currents generated by the star's interior fluids spiraling faster and faster. But spinning too fast introduces centrifugal forces that threaten to tear the star apart. Balancing this spin, the magnetic field strength, and the star's gravitational cohesion requires a cosmic dance on a knife's edge, where the slightest imbalance could lead to catastrophic collapse or explosion. Moreover, the magnetic field itself can distort the star's shape. Rather than a perfect sphere, a hypermagnetar might be stretched into an oblong or even more irregular form, deformed by the stresses of its own magnetism. This distortion would affect the star's gravitational field, its spin stability, and its ability to maintain the magnetic currents generating the field. The entire system becomes a complex, intertwined web of forces, each influencing the other in ways that challenge current physics models. From a quantum perspective, fields this strong begin to affect the vacuum of space itself. At magnetic strengths approaching or exceeding the so-called quantum critical field, around 4.4 times 10 to the power of 13 Gauss, the vacuum behaves like a polarizable medium, bending light and enabling exotic particle interactions. A hypermagnetar's field would be far beyond this threshold, potentially warping spacetime and matter in ways not yet observed or understood, opening the door to new physics, phenomena that might require entirely new theories to describe. These theoretical challenges make the hypermagnetar not just an astrophysical curiosity, but a profound test for fundamental physics. To understand how such an impossible magnet could exist, scientists must push the limits of nuclear physics, quantum mechanics, and general relativity. The hypermagnetar forces us to confront gaps in our understanding and inspires searches for new physics beyond the standard model. In summary, maintaining a magnetic field trillions of times stronger than any known star strains the very fabric of stellar structure. It challenges the balance of forces that hold stars together, demands exotic states of matter and energy, and possibly alters the fundamental laws of physics as we know them. The hypermagnetar is not just the most dangerous star conceivable. It is a cosmic riddle, a monstrous enigma pushing the boundaries of science and imagination alike. The origins of a hypermagnetar, a star so extreme it defies our understanding, lie in some of the universe's most violent and energetic phenomena. To speculate about how such a cosmic beast could be born, we must turn our gaze to the cataclysmic death throes of supermassive stars and the extraordinary explosions known as hypernovae. These events are rare, powerful, and capable of concentrating vast energies into an incredibly small space, possibly setting the stage for a hypermagnetar's birth. A hypernova is an explosive stellar death beyond the scale of a typical supernova. While a supernova marks the violent collapse of a massive star's core followed by an immense explosion, a hypernova is an even more energetic event, releasing up to 10 times the energy of a conventional supernova. It usually occurs when a star over 30 times the mass of our Sun exhausts its nuclear fuel. Without the outward pressure from fusion to counterbalance gravity, the star's core collapses rapidly under its own immense weight. The result is a violent implosion followed by a colossal explosion, ejecting most of the star's outer layers at speeds approaching a significant fraction of the speed of light. This collapse and explosion create the extreme conditions necessary for forging exotic remnants like neutron stars or black holes. In the case of a hypermagnetar, the hypernova's energy isn't merely released outward, it's also trapped and compressed within the collapsing core, amplifying magnetic fields to unparalleled intensities. During the core collapse, the star's internal magnetic field lines become twisted and compressed as the matter is crushed into a neutron star-sized object roughly 20 kilometers across but containing more mass than our Sun. The conservation of magnetic flux means that as the star's radius shrinks dramatically, the magnetic field strength skyrockets. However, a hypermagnetar takes this process to a staggering extreme. The collapse must occur under conditions far more intense than typical neutron star formation. Perhaps the progenitor star was rotating at an extraordinary rate, causing the core's magnetic dynamo to spin up like an accelerator, amplifying magnetic fields to strengths 1 trillion times stronger than the usual magnetars. The collapse may also funnel and trap energy more efficiently, compressing it into the newborn star's interior and igniting magnetic fields of unprecedented power. The hypernova's explosive power doesn't simply vanish after the blast. Instead, the remaining core, this hypermagnetar, is left spinning with near breakup velocity, surrounded by a cloud of expelled stellar material that may form nebulae or accretion disks. This rapid rotation, combined with the extraordinary magnetic field, could stabilize the hypermagnetar against collapse into a black hole, allowing it to exist as an ultra-magnetized neutron star. The balance between gravity trying to crush the star further and the magnetic and rotational pressures pushing outward creates a precarious equilibrium, a cosmic tightrope walk. During this violent birth, the hypernova may also release intense gamma-ray bursts, some of the most luminous electromagnetic events in the universe. These bursts are thought to arise from jets of matter propelled at relativistic speeds along the star's rotation axis. The connection between gamma-ray bursts and magnetars is an area of active research, and the hypermagnetar hypothesis suggests that some of the most energetic gamma-ray bursts could be direct signatures of these ultra-magnetized remnants forming. While direct observation of hypermagnetars remains elusive, astronomers have observed magnetars forming after some supernovae and hypernovae, suggesting that this pathway is plausible. Theoretically, only the most massive stars with the right combination of rapid rotation, strong initial magnetic fields, and particular core compositions could undergo this extraordinary transformation. Any deviation from these conditions might result in a black hole or a less extreme neutron star, underscoring how rare and exotic hypermagnetars must be. Moreover, the hypernova that bursts a hypermagnetar may leave unique signatures in the surrounding space. Shock waves propagating through the interstellar medium, enriched with heavy elements from the exploded star, can produce nebulae that glow in specific wavelengths. These remnants might offer indirect clues to the presence of a hypermagnetar, though teasing out these signals amid the crowded cosmic background is a formidable challenge. In essence, the hypermagnetar's birth is the ultimate crescendo of stellar evolution and death, where the most massive stars end their lives in a blaze of energy so intense it can forge a star capable of ripping atoms apart across light years. The hypernova acts as the cosmic forge, compressing matter and magnetic fields into an ultra-dense, ultra-magnetized core, a star born from destruction, a monster forged in the most extreme crucible the universe can offer. This violent origin story is crucial for understanding not just the hypermagnetar itself but the environment around it, an environment marked by turbulence, radiation, and leftover stellar debris that can continue to affect neighboring systems. As the hypermagnetar spins down over millennia, it remains a testament to the extraordinary forces unleashed by hypernovae, a lingering, terrifying echo of stellar death capable of shaping entire regions of the galaxy. The birth of a hypermagnetar through a hypernova explosion is only the beginning of its transformation into one of the most violent and destructive objects the universe could conceive. Central to this transformation is the star's rapid rotation, a furious spin that acts like a cosmic dynamo, further amplifying its already unimaginable magnetic field. This spin doesn't just make the hypermagnetar a passive leftover of a star's death. It turns it into a deadly engine of destruction whose effects ripple across light years of space. Imagine a figure skater pulling in their arms during a spin, accelerating faster and faster as they shrink their radius. This simple analogy applies on an incomprehensibly massive scale to a hypermagnetar. As the core of the progenitor star collapses from thousands of kilometers across to a mere 20 kilometers or less, the conservation of angular momentum demands that the newly formed neutron star spins at a breathtaking rate. Instead of a leisurely rotation taking hours or days, these stellar remnants can complete a rotation in milliseconds. Some known magnetars spin once every few seconds, but hypermagnetars might rotate hundreds or even thousands of times per second, turning like titanic cosmic turbines. This rapid rotation is not merely a fascinating detail. It is a critical ingredient in the amplification of the magnetic field itself. The star's interior is a turbulent sea of charged particles, superfluid neutrons, and possibly exotic states of matter. The interaction of these fluids and particles with the star's rotation drives powerful dynamos, complex electrical currents that twist and amplify magnetic fields. In a hypermagnetar, the dynamo effect is pushed to such extremes that the magnetic field strength is multiplied many times over what would be possible in a slower spinning star. The physics of this dynamo process is intricate. Within the star's interior, differential rotation means different layers spin at varying speeds. This shearing motion stretches and winds magnetic field lines, intensifying them dramatically. Additionally, turbulent convection, massive flows of energy and matter within the star, stirs the magnetic field, generating complex and chaotic structures. These processes combine to create a magnetic field not just of immense strength but also of immense complexity, with twisted knots and loops of magnetic energy coiling like invisible serpents around the star. The consequences of this rapid spin and magnetic amplification are profound. A hypermagnetar becomes a veritable powerhouse of electromagnetic energy, capable of releasing sudden and violent bursts of gamma rays and X-rays. These bursts arise from the star's magnetic field lines snapping and reconnecting in violent flares, akin to solar flares on the sun but amplified to unimaginable scales. The energy released in a single flare could outshine an entire galaxy for a brief moment, bathing vast regions of space in lethal radiation. Moreover, the rapid spin drives powerful winds of charged particles, streams of electrons, protons, and atomic nuclei accelerated to near light speed. These winds carve out vast bubbles in the surrounding interstellar medium, sweeping away gas and dust and shaping the environment around the hypermagnetar. This activity can prevent new stars and planets from forming nearby, creating a barren region of space where life would be impossible. The rotational energy of a hypermagnetar also decays over time. As the star spins, electromagnetic radiation carries away angular momentum, causing the rotation to slow gradually over thousands or millions of years. This spin-down releases enormous amounts of energy, fueling continuous emissions of radiation and particle winds. The star effectively converts its rotational energy into destructive power radiated outwards. This gradual loss of spin also plays a role in the star's stability. If the hypermagnetar were to spin down too quickly or unevenly, it could destabilize its magnetic field or its shape, potentially triggering catastrophic starquakes, massive ruptures in the star's crust that release further bursts of energy. These quakes could also temporarily alter the star's rotation, leading to complex feedback between spin, magnetic field, and structural stability. The interaction between the hypermagnetar's rapid spin and its magnetic field also affects the spacetime around it. The star's intense gravity, combined with its rotation, can twist spacetime itself in a phenomenon known as frame dragging, predicted by Einstein's theory of general relativity. In the vicinity of such a rapidly spinning and magnetized object, the normal rules of physics are bent, warped, and distorted, affecting how light and matter move. For any objects or particles caught near the hypermagnetar, this spin-induced magnetism creates a violent environment where charged particles are accelerated to extreme energies, emitting intense radiation as they spiral along magnetic field lines. These processes contribute to the hypermagnetar's reputation as a cosmic predator, capable of sterilizing vast regions of space through both direct magnetic influence and the radiation it generates. The rapid spin also means that the hypermagnetar's magnetic axis may not align with its rotation axis. This misalignment causes the magnetic poles to sweep through space like lighthouse beams, creating periodic pulses of radiation detected by distant observers as pulsars. Hypermagnetars, with their extreme magnetic fields and rapid rotation, could emit the most powerful and energetic pulses in the cosmos, signals that might be observed as ultraluminous fast radio bursts or extreme gamma-ray pulses. Understanding the spin of doom is critical to appreciating just how dangerous and dynamic a hypermagnetar can be. It's not merely a static object sitting quietly in space. It's a whirling vortex of energy and magnetism, its rotation fueling a relentless cycle of destruction. This spin amplifies the magnetic field beyond all known limits and powers the star's ability to disrupt matter and energy on scales that dwarf anything seen in conventional astrophysics. In this sense, the hypermagnetar's rapid rotation is both its strength and its curse. It allows the star to maintain its hyper-strong magnetic field, but it also creates instability and drives violent outbursts of radiation. The interplay of spin and magnetism makes the hypermagnetar a cosmic dynamo of destruction, a star whose very existence challenges the limits of physics and whose behavior defies easy prediction. As we contemplate the hypermagnetar spinning silently in the darkness of space, remember that its furious rotation is not just a characteristic, it is the engine that powers its reign of terror. This spin of doom ensures that the hypermagnetar is not just the most dangerous star in the universe but also one of the most fascinating enigmas, where gravity, magnetism, and motion collide in a cosmic dance of ultimate power. The cosmos is a theater where some of the most extreme forces known to science perform a spectacular, and often deadly, dance. Among the most formidable of these performances is the interplay between gravity and magnetism in the heart of a hypermagnetar. To truly grasp the terrifying power of this star, we must explore how these two titans of nature, immense gravitational pull and lethal magnetic fields, combine and interact to create a celestial entity unlike any other. Gravity, the force that binds stars, planets, and galaxies together, is the fundamental architect of stellar life cycles. In neutron stars, gravity's role is elevated to an extraordinary level. After a massive star exhausts its nuclear fuel, its core collapses under gravity's unyielding grip, compressing matter so densely that a teaspoon of neutron star material would weigh billions of tons on Earth. This extreme compression warps spacetime itself, creating gravitational fields intense enough to bend light and slow time near the star's surface. Magnetism, on the other hand, is the force arising from moving electric charges, manifesting as magnetic fields that influence charged particles and the behavior of matter. While magnetic fields are common across the universe, from the gentle pull of Earth's magnetosphere to the blistering fields of pulsars, none approach the monstrous scale found in magnetars. And a hypermagnetar takes this scale to the extreme, wielding magnetic fields trillions of times stronger than those in ordinary magnetars. When gravity and magnetism meet in such extraordinary intensities, their combined effect becomes more than the sum of their parts. Gravity relentlessly pulls matter inward, striving to compress the star into an even denser state, potentially forming a black hole. Meanwhile, the hypermagnetar's magnetic field pushes outward with such ferocity that it resists collapse, distorting matter and even spacetime around it. This tension between the inward force of gravity and the outward pressure of magnetic field shapes the star's very existence and behavior. The star's immense gravity creates an environment where space and time themselves are curved, affecting how magnetic fields propagate. Near a hypermagnetar, magnetic field lines do not stretch out evenly but warp along the curves of spacetime. This warping can intensify local magnetic field strengths even further, leading to regions where the magnetic force is concentrated into loops and knots of energy. These concentrations are unstable and prone to sudden rearrangements, or magnetic reconnection, events, which unleash tremendous bursts of energy. At the same time, the hypermagnetar's gravity influences the movement of charged particles trapped within its magnetic field. Electrons and protons spiral along field lines, accelerated by electromagnetic forces to near light speeds. Gravity confines these particles closer to the star's surface, creating dense magnetospheres filled with high-energy plasma. The interplay between gravitational confinement and magnetic acceleration produces intense radiation emissions, X-rays and gamma rays, that can be detected across vast cosmic distances. The structural integrity of the hypermagnetar itself is a delicate balancing act between these opposing forces. gravity attempts to compress the star further, pushing matter to extremes where exotic states like quark-gluon plasma may emerge. Magnetic fields resist this compression, exerting enormous pressure that can deform the star into elongated or irregular shapes rather than a perfect sphere. These distortions affect the star's rotation and can induce starquakes, fractures in the neutron star's crust, that release sudden bursts of energy. This battle between gravity and magnetism also governs the star's lifespan and stability. Should gravity win, the star could collapse into a black hole, swallowing all the magnetic energy within an event horizon and rendering it undetectable by electromagnetic means. If magnetism maintains its grip, the hypermagnetar endures as an ultra-magnetized neutron star, radiating intense energy and exerting destructive influence over its surroundings. Moreover, the combined fields shape the star's influence on nearby matter and space. The gravitational pull draws in dust, gas, and even entire star systems if they venture too close, while the magnetic field can strip atmospheres from planets and stars, distort stellar winds, and create immense voids in the interstellar medium. This dual influence extends the hypermagnetar's deadly reach far beyond its physical radius. In the context of spacetime, the interaction of gravity and magnetism near a hypermagnetar may produce exotic phenomena predicted by advanced physics theories. For instance, frame dragging, a process where the star's rotation drags the surrounding spacetime, could interact with magnetic fields to produce complex field geometries and energetic particle jets. These jets, blasting out at near-light speeds, can carve enormous cavities in space and bombard distant regions with lethal radiation. In essence, gravity and magnetism in a hypermagnetar are locked in a cosmic tug-of-war, shaping an object whose destructive powers are magnified beyond ordinary comprehension. This synergy makes the hypermagnetar not just a stellar remnant, but a dynamic, volatile force that warps matter, energy, and spacetime itself. Understanding this intricate interplay challenges our deepest physical theories and pushes astrophysics into realms where quantum mechanics, relativity, and electromagnetic theory converge. It is a frontier where the universe's most fundamental forces are tested against one another in a spectacular and terrifying show of cosmic power. This fusion of immense gravity and lethal magnetism is what cements the hypermagnetar's place as the universe's ultimate cosmic predator, a star that does not merely exist but dominates, distorts, and destroys everything that dares come within its grasp. Imagine drifting through the vast expanse of interstellar space, a seemingly infinite ocean of stars, planets, and cosmic dust stretching endlessly in every direction. You are aboard a spacecraft, moving silently and cautiously among the familiar points of light, perhaps exploring the unknown or charting distant worlds. Suddenly, without warning, you cross an invisible boundary, an unseen sphere that marks the outer edge of a domain of destruction unlike anything else in the universe. This is the death zone of a hypermagnetar, a vast, intangible shell of annihilation that extends for light years around the star, silently waiting for any matter that dares to venture too close. This death zone is not marked by glowing gas clouds or visible shockwaves. There is no fiery halo or radiation beacon announcing its presence. Instead, it is an invisible prison of magnetism, where the very fabric of matter and energy is subjected to forces so immense that atoms cannot hold together, molecules unravel, and electrons are ripped free from their nuclei. This sphere, stretching across unimaginable distances, is a silent killer, an unseen hazard lurking in the darkness of space, ready to obliterate anything that crosses its boundary. Within this death zone, the rules that govern the universe begin to break down. The hypermagnetar's magnetic field stretches out in tendrils far beyond the star's physical surface, warping and twisting the space around it. These invisible magnetic lines of force ensnare anything that crosses into the zone: dust grains, rogue asteroids, planets, even entire star systems, exposing them to unrelenting forces that shred their atomic structure. Imagine a lone planet crossing into this zone. Initially, it appears as a solid world, but as it ventures deeper, the hypermagnetar's magnetism begins to disrupt the chemical bonds holding molecules together. Oceans boil off into charged plasma, rocks fracture at the molecular level, and the atmosphere is stripped away as electrons are ripped free and swept into the magnetic currents. Eventually, What was once a vibrant world becomes a ghostly cloud of ionized gas, spread thin across the star's invisible magnetic prison. Even light itself bends and shifts within this sphere. Photons traveling through the hypermagnetar's magnetic field experience distortions and polarization effects, making distant stars shimmer strangely or vanish from view entirely. This optical distortion adds another layer of mystery, masking the death zone from conventional observation and making it appear as a void where nothing should be. The death zone also acts as a shield, preventing matter from approaching the hypermagnetar's core. Like a force field, the magnetic pressure pushes back against infalling gas and dust, halting the formation of accretion disks or planetary bodies nearby. This region of space remains eerily empty, a desolate void where the chaotic interplay of magnetic and gravitational forces forbids life and matter from taking hold. Within this vast sphere, bursts of gamma rays and X-rays periodically erupt from the star's surface, sending waves of deadly radiation pulsing outward. These flares light up the death zone with brief, violent flashes that can travel across entire star systems, frying electronics, breaking molecular bonds, and sterilizing any life unlucky enough to be caught in their path. The death zone's sheer scale is staggering. It could extend for dozens, hundreds, or even thousands of light years from the star, encompassing entire solar systems within its lethal embrace. For perspective, our own solar system extends about 1 to 2 light-years in the distant Oort cloud, and a hypermagnetar's death zone could easily engulf volumes of space several times that size. To any observer, or any unfortunate traveler, this sphere is an invisible minefield, a silent cosmic predator's territory where the slightest misstep leads to inevitable annihilation. No warning signals, no beacon of danger, just the quiet, relentless reach of magnetism, warping matter and energy, erasing anything that crosses its threshold. This death zone embodies the ultimate cosmic paradox, a star whose presence is both invisible and all-encompassing, whose power radiates not through visible flame but through unseen forces that can unmake the very building blocks of reality. It is a silent sentinel of destruction, a sphere of oblivion where space itself becomes hostile and uninhabitable. The existence of such a death zone forces astronomers and astrophysicists to rethink how we map and understand the galaxy. It challenges our assumptions about empty space and warns of hidden dangers that might lurk in the darkness between stars, invisible yet deadly. This invisible sphere could explain mysterious disappearances of matter or strange distortions in observed light, clues hinting at the presence of a hypermagnetar lurking somewhere in the vast cosmic wilderness. In contemplating this death zone, we are reminded of the universe's immense scale and its capacity for both creation and destruction. The hypermagnetar's sphere of annihilation is a stark testament to the raw, unyielding forces at play on the grandest scales, forces that can silently, invisibly, and utterly erase worlds, systems, and possibly entire regions of space. As we gaze upward into the night sky, the stars twinkling serenely, it is humbling and chilling to consider that among them might lie these invisible killers, silent spheres of death, patiently waiting in the darkness, guardians of cosmic oblivion, whose reach can stretch light years, erasing anything that dares to wander into their domain. Beyond the overwhelming magnetic power that defines a hypermagnetar, there exists another equally formidable, though more familiar, cosmic force at play: gravity. While the magnetic field acts invisibly and relentlessly over vast distances, ripping atoms apart from light years away, gravity operates with a devastating, physical grip that can stretch, distort, and utterly tear apart any matter daring enough to approach close. This dual assault, magnetism on an atomic scale and gravity on a macroscopic scale, makes the hypermagnetar not just a source of radiation and atomic destruction but also a celestial crusher capable of shredding entire objects by sheer tidal force. Tidal forces arise due to the gravitational gradient experienced by an object in the presence of a massive body. In simpler terms, the side of the object closer to the massive star feels a stronger gravitational pull than the side farther away. This difference creates a stretching effect along the line toward the massive body. On Earth, tidal forces from the Moon cause our ocean tides, gently pulling and releasing vast bodies of water. Near a hypermagnetar, these forces are amplified unimaginably, becoming a relentless, crushing grip that can distort solid matter until it tears apart. Imagine an asteroid or a small moon venturing near the hypermagnetar's death zone. As it draws closer, the star's immense gravitational field begins to tug on it unevenly. The side facing the star feels a stronger pull, stretching it outward, while the far side lags behind. This results in tidal stress that deforms the object, elongating it like a cosmic taffy being pulled in opposite directions. If the gravitational difference is large enough, and near a hypermagnetar, it certainly is, this stretching can exceed the structural integrity of the object, causing it to fracture and disintegrate. For objects larger than asteroids, planets, or even small stars, the tidal effects are even more catastrophic. Planets are held together by gravity and material strength, but these forces pale in comparison to the hypermagnetar's gravity. As a planet approaches the star, the intense tidal forces can stretch it so severely that its surface cracks and fissures open, releasing internal heat and triggering massive geological upheavals. Volcanic activity, earthquakes, and atmospheric loss would follow rapidly, transforming the once stable world into a boiling, fragmented ruin. If the planet moves even closer, the tidal forces can surpass the planet's self-gravity, causing it to be pulled apart completely in a process known as spaghettification, named for the way matter is stretched into long, thin strands. This gruesome effect isn't just theoretical. It's been observed near black holes, where the tidal forces are strong enough to shred stars that stray too close. The hypermagnetar's intense gravity creates a similar, if not more violent, tidal environment around itself. In addition to stretching and tearing, tidal forces can cause intense heating within the object, known as tidal heating. As the star's gravity flexes the interior of a planet or moon, friction generates internal heat that can melt rock, drive volcanic activity, and alter the chemical makeup of the surface and atmosphere. This process can sterilize any potential life and accelerate the planet's destruction even before it is physically torn apart. Interestingly, the interaction of tidal forces and the hypermagnetar's magnetic field can produce additional complex effects. The star's magnetic field can induce electric currents in conductive materials of a passing body, leading to further heating and weakening of the structure. This electromagnetic induction combined with gravitational stretching accelerates the disintegration process. For smaller objects like comets, asteroids, or spacecraft, tidal forces near a hypermagnetar are no less deadly. The intense gradient can fracture the hull of a spacecraft, disable critical systems, and scatter debris across the space around the star. For any object unprepared for such an environment, survival is impossible. The gravity of a hypermagnetar is so strong that it warps spacetime significantly, affecting not only matter but also light and electromagnetic signals. This curvature can trap radiation and particles in complex orbits, further intensifying the hazardous environment close to the star. Objects trapped in these zones may be subjected to prolonged exposure to both tidal stresses and magnetic destruction. The region around the hypermagnetar where tidal forces dominate extends beyond its physical surface, overlapping and interacting with the magnetic death zone. This combined sphere of influence is a vast, invisible trap for any wandering matter in space. Once an object crosses into this domain, it faces simultaneous atomic disintegration and macroscopic destruction, ensuring that nothing escapes intact. In essence, the hypermagnetar's tidal forces add a brutal physical dimension to its destructive repertoire. While magnetism operates on the atomic and subatomic scale, gravity imposes catastrophic mechanical stresses on objects, ripping apart everything from dust particles to planets. Together, they make the hypermagnetar a multifaceted predator in the cosmic wilderness, capable of annihilating matter both at the smallest and largest scales. This tidal tearing is not a slow process. It can happen swiftly, with planets breaking apart in hours or days once they cross a critical threshold. The debris from these tidal disruptions can form spectacular and violent rings of matter around the hypermagnetar, swirling in a chaotic dance before eventually being drawn into the star or ejected by magnetic winds. Through the combined devastation of magnetism and tidal gravity, the hypermagnetar enforces its sovereignty over a vast region of space, turning what might otherwise be a starry neighborhood into a graveyard of shattered worlds and dispersed atoms. It is a cosmic force so overwhelming that it defies simple analogy, blending the microscopic horrors of atomic disruption with the macroscopic cataclysms of gravitational destruction. This duality of destruction, the invisible but all-consuming magnetic annihilation paired with the crushing, ripping tidal forces, places the hypermagnetar beyond the realm of ordinary cosmic phenomena. It is not just a star, it is an engine of obliteration, a force field of death, and a stark reminder of the universe's capacity for both wonder and terror. Beyond the catastrophic destruction of planets and stars by crushing gravity and blistering radiation, the hypermagnetar's influence reaches even further, into the very fabric of matter itself, tearing apart the molecular bonds that hold the universe's building blocks together, across distances spanning light years. This is destruction on a scale so fundamental and vast that it challenges our deepest understanding of chemistry, physics, and the fragile balance that allows matter, and ultimately life, to exist. To understand this, we must first appreciate what molecules are, assemblies of atoms bonded by electromagnetic forces, holding together through shared electrons and specific energy states. These bonds, covalent, ionic, metallic, are what form the solids, liquids, gases, and complex organic compounds that populate the cosmos. Even the simplest molecule, like hydrogen gas, H2, is held together by delicate energy interactions that, under extreme external forces, can be broken. Normally, molecular bonds are stable across the vast voids of interstellar space, protected by the relative calm and low-energy environment. While radiation and cosmic rays occasionally disrupt molecules, allowing chemistry to proceed and new molecules to form, the processes are gradual and localized. But near a hypermagnetar, the situation is dramatically different. The hypermagnetar's magnetic field isn't just a force that influences charged particles. At its unprecedented strength, it warps and distorts electromagnetic interactions themselves. The bonds between atoms and molecules rely on these electromagnetic forces to keep electrons shared or transferred in predictable patterns. When subjected to the hypermagnetar's trillion times stronger than normal magnetic field, these interactions are violently disturbed. Imagine a vast region of space suffused with a magnetic field so intense it overwhelms the internal forces holding molecules intact. Electrons, the glue of molecular bonds, are torn free, spiraling along magnetic field lines or ejected entirely from their atomic orbits. Without electrons, atoms cannot maintain their connections, and molecules unravel. This process turns what was once solid, liquid, or gaseous matter into a diffuse, ionized plasma of stripped nuclei and free electrons. This unraveling is not limited to solids or nearby planets, but extends far into interstellar space, across distances of many light years. Dust grains, tiny solid particles composed of silicates, carbon compounds, or ices, disintegrate at the molecular level. Complex organic molecules, precursors to life as we know it, are reduced to their atomic components. Even molecular clouds, vast accumulations of gas and dust where stars and planets form, are at risk of being sterilized and dispersed. The implications are staggering. Regions within the hypermagnetar's reach become chemically barren zones where the formation of new stars, planets, and ultimately life, is effectively halted. The usual cosmic recycling of matter, where supernova remnants seed star-forming regions with heavy elements, is disrupted or entirely prevented within these zones of molecular destruction. Moreover, this molecular destruction doesn't proceed quietly. As molecules break apart, the resulting free electrons and ions interact violently with the magnetic and electromagnetic fields, producing bursts of radiation across the spectrum. These emissions further ionize surrounding matter, creating expanding shells of charged particles and radiation that can sweep across neighboring star systems. Even the cold depths of space, once thought to be tranquil, are thus transformed into turbulent fields of energetic particles and radiation, rendering the environment hostile to complex chemistry and biology. The hypermagnetar's molecular destruction zone becomes a vast no-man's land of atomic debris and radiation, a far-reaching corona of annihilation extending light years beyond the star itself. In practical terms, this means that entire star-forming regions near a hypermagnetar would be chemically sterilized, their molecular clouds dispersed or broken down before they can collapse into new stars or planets. This represents a significant cosmic feedback mechanism, where the hypermagnetar's presence influences the galactic ecosystem, suppressing star formation and altering chemical evolution over immense scales. From an observational standpoint, astronomers might detect these effects indirectly. Regions with unexplained molecular depletion, unusual ionization signatures, or disrupted chemical compositions could hint at the presence of a hypermagnetar's influence. Spectral lines from molecular gases would be faint or absent, replaced by emission from highly ionized plasma. Such anomalies could mark the invisible boundary of the hypermagnetar's molecular destruction zone. The sheer scale of this molecular disintegration underscores the hypermagnetar's unique role in the cosmic landscape. It is not merely a star emitting powerful radiation or a gravity well pulling in matter. It is a star that unravels the very chemistry that makes matter cohesive, transforming entire regions of space into sterile voids of atomic fragments. This molecular destruction across light years is a silent but profound force. It erases the chemical fingerprints of cosmic history, wipes out the raw materials for life, and disrupts the cycle of matter that fuels galactic evolution. It is a reminder that the universe is not a passive backdrop, but a dynamic arena where forces of unimaginable strength sculpt the fate of matter and life itself. In contemplating this, we come to see the hypermagnetar not just as an astronomical curiosity but as a cosmic arbiter, one whose presence dictates where life can and cannot arise, where chemistry can flourish or is extinguished, and where the delicate dance of atoms and molecules is violently ended. It is a star that redefines destruction, stretching across space and time to tear apart the molecular threads that weave the fabric of the cosmos. The universe is vast, filled with countless stars that illuminate the night sky, their light traveling across unimaginable distances to reach our eyes. We are accustomed to gauging the presence of celestial objects by their brightness, color, or the effects they have on nearby matter. Yet, the most dangerous star imaginable, a hypermagnetar, could defy all these expectations by being completely invisible to the naked eye. It might lurk silently in the darkness, hidden among the countless pinpricks of starlight, waiting for the unsuspecting to wander too close before revealing its deadly nature. Unlike typical stars, which glow brightly because of the nuclear fusion reactions in their cores, a hypermagnetar is a neutron star, an incredibly dense remnant of a once massive star that has exhausted its fuel and collapsed. Neutron stars themselves are faint invisible light, often observable only through their emissions in radio waves, X-rays, or gamma rays. Hypermagnetars, with their extreme magnetic fields and violent environments, might emit sporadic bursts of high-energy radiation, but these signals could be rare, brief, or obscured by intervening dust and gas. This invisibility poses a profound challenge for astronomers and space explorers. The hypermagnetar's physical size is tiny by stellar standards, only about 20 kilometers in diameter, yet its magnetic influence extends across light years. The star itself might be hidden in a dark corner of the galaxy, nestled within dense molecular clouds or behind thick curtains of interstellar dust that block visible light. From Earth, it could appear as nothing more than an empty patch of sky. Even sophisticated telescopes might miss it unless they happen to catch its elusive radiation flares or detect subtle distortions in nearby stars' light. But by then, it might be too late for anything within its immense death zone. This invisible threat silently shapes and destroys its surroundings without warning, a cosmic predator hiding in plain sight. Imagine a spaceship navigating a seemingly safe region of space, relying on sensors and telescopes to detect hazards. A hypermagnetar lurking just beyond the visible spectrum could evade all detection, its magnetic and gravitational forces pulling at the vessel's structure and systems long before the crew realizes the danger. Electronic instruments might begin to malfunction inexplicably, navigation systems could fail, and yet the source of the disturbance remains hidden. On a larger scale, entire star systems might exist near a hypermagnetar without knowing it. Planets orbiting faint companion stars could experience atmospheric stripping, radiation poisoning, or molecular breakdowns, all without the presence of a visible stellar threat. To the casual observer, these effects might appear as natural anomalies or unexplained cosmic phenomena, masking the true cause lurking in the shadows. The invisibility of a hypermagnetar also complicates efforts to understand the galactic environment. Astronomers mapping stellar populations and interstellar matter may overlook regions rendered barren or distorted by the star's influence, attributing the changes to other, less dramatic causes. This hidden presence could skew our understanding of star formation rates, chemical distribution, and cosmic evolution. The concept of an invisible cosmic killer challenges the very notion of safety in space. It reminds us that our observational tools, while powerful, have limits, especially when faced with phenomena that defy conventional detection. In the darkness beyond the reach of our instruments, a hypermagnetar could lie in wait, its presence betrayed only by the destruction it leaves in its wake. Such invisibility transforms the hypermagnetar from a distant curiosity into a lurking menace, a celestial ghost that haunts the galaxy. It raises unsettling questions. How many such objects might be hidden within our own Milky Way? Could one be drifting closer without our knowledge? Are there silent regions of space where matter disappears, consumed by an unseen magnetic titan? This invisible threat demands a reevaluation of our cosmic vigilance. It urges the development of new detection methods, more sensitive instruments, and refined models to uncover the hidden forces shaping our universe. It also serves as a stark reminder that in the vastness of space, what we cannot see may be far more dangerous than what we can. Ultimately, the hypermagnetar's invisibility is part of what makes it so terrifying. It does not announce its presence with a blazing light or a roaring burst. Instead, it waits silently in the shadows, a phantom star whose deadly reach extends unseen across the cosmos. When its destructive influence finally reveals itself, the devastation is swift, absolute, and irreversible. The notion of such an invisible destroyer lurking in the galaxy is a haunting thought. It transforms the starry night sky, from a map of light and life, to a veil concealing potential annihilation. And as we peer into the cosmos, we must acknowledge that the universe holds dangers not just in what shines brightly, but also in the darkness where even stars can vanish from sight, waiting for the moment to unleash their catastrophic power. The presence of a hypermagnetar in proximity to other stars introduces a series of catastrophic effects that ripple through neighboring systems, fundamentally altering the architecture and stability of stellar environments in ways that challenge our very understanding of star system dynamics. Unlike typical cosmic interactions where stars influence each other through gravity, radiation, or occasional stellar winds, the hypermagnetar introduces an extreme agent of chaos, a magnetic and gravitational force so immense it can literally strip away atmospheres, destabilize orbits, and disrupt the delicate balance that allows solar systems to exist. First, consider the effect on the atmospheres of nearby stars and their planets. Stars, especially younger and less massive ones, can be surrounded by extended layers of ionized gases, plasma, that form their coronae and stellar winds. These winds play a crucial role in shaping planetary atmospheres, the formation of comet tails, and the dispersal of cosmic dust. However, the hypermagnetar's overwhelming magnetic field and radiation pressure would interact destructively with these stellar winds. Magnetic reconnection events, where the magnetic fields of the hypermagnetar and a nearby star meet and realign, could unleash bursts of energy that strip away the outer layers of a star's atmosphere. This process is akin to an intense solar flare but magnified to cosmic proportions, effectively peeling back layers of a star's gaseous envelope over time or during sudden, violent bursts. For planets orbiting these affected stars, the consequences are dire. A stripped stellar atmosphere reduces the shielding that protects planetary atmospheres from cosmic radiation. The increased exposure to energetic particles, gamma rays, and charged ions emitted by the hypermagnetar would erode planetary atmospheres, leading to atmospheric collapse and loss of surface water, key ingredients for life as we know it. Over extended periods, this stripping could sterilize entire planets, leaving barren, lifeless rocks orbiting stars that have themselves been weakened by magnetic interactions. The destabilization goes deeper. A star's magnetic field plays a subtle but essential role in maintaining the dynamics of its system. It influences the behavior of charged particles in the stellar wind and can affect the rotation rate and magnetic braking of the star itself. When a hypermagnetar's immense field intrudes, it can induce fluctuations and disruptions in these magnetic cycles, causing variability in stellar activity. This can lead to irregular bursts of radiation, flares, or unexpected changes in luminosity that ripple through the system. Furthermore, the gravity of the hypermagnetar, though not as extreme as a black hole's, is still intense enough to perturb the orbits of stars and their planets, especially if the hypermagnetar drifts relatively close. Gravitational interactions can trigger orbital eccentricities, pulling planets into elliptical orbits that expose them to extreme temperature swings, tidal heating, or even ejection from the system entirely. In multiple star systems, the hypermagnetar's gravity could disrupt the orbital dance, causing stars to collide, merge, or fling planets into interstellar space. In star clusters, where stars exist in closer proximity, a hypermagnetar's destructive influence can cascade. Its radiation and magnetic storms could initiate chain reactions, where destabilized systems begin to interact violently with their neighbors, amplifying the destruction across a wide region of space. The star cluster could become a graveyard, with disrupted orbits, stripped atmospheres, and a barren interstellar medium devoid of the dense molecular clouds necessary for new star formation. Additionally, the hypermagnetar's gamma-ray flares and electromagnetic outbursts can induce significant ionization in nearby interstellar gas, altering its chemical composition and inhibiting the cooling processes required for cloud collapse and star birth. This means entire regions could become star formation deserts, where the presence of a hypermagnetar suppresses the birth of new stars for millions of years, shaping the evolutionary trajectory of the galaxy. On a more detailed level, the interaction between the hypermagnetar's magnetic field and the magnetic environments of nearby stars can lead to complex phenomena like magnetic reconnection, field line entanglement, and plasma acceleration. These processes generate highly energetic particles that not only damage atmospheres but also increase the cosmic radiation background, posing hazards to any potential life forms or advanced civilizations. The cumulative effect of all these forces paints a picture of the hypermagnetar as a cosmic disruptor of unparalleled scale, capable of stripping atmospheres, destabilizing orbits, altering stellar evolution, and sterilizing vast swaths of space. It transforms tranquil star systems into chaotic, hostile environments where the normal cycles of birth, life, and death of stars and planets are violently interrupted or permanently ended. From the perspective of life's potential, the hypermagnetar's influence is a profound obstacle. The fragile conditions needed for habitability, stable orbits, protective atmospheres, and moderate radiation levels are compromised or destroyed within its sphere of influence. This makes regions around the hypermagnetar inhospitable, effectively carving out dead zones where life cannot emerge or survive. Astronomically, the presence of such a star could explain puzzling observations, systems with missing atmospheres, irregular stellar activity, or disrupted orbital mechanics might bear the invisible fingerprint of a hypermagnetar lurking nearby. Its influence could also account for sudden star formation halts in certain regions, the unexpected sterilization of star-forming clouds, or the presence of high-energy cosmic rays without a clear source. In conclusion, the hypermagnetar's impact on nearby stars extends far beyond mere proximity danger. It actively reshapes the cosmic neighborhood, stripping atmospheres, destabilizing orbits, and disrupting the delicate balance necessary for star system stability and life. It acts as both a destructive force and a cosmic sculptor, reshaping galactic environments with its invisible but overwhelmingly potent magnetic and gravitational reach. The existence of a hypermagnetar within our own galaxy would represent not just a localized danger but a profound galactic hazard, an invisible force field of annihilation stretching across light years, rendering entire regions inhospitable to life and fundamentally altering the cosmic landscape. To truly grasp the magnitude of this threat, we must consider the scale and scope of the hypermagnetar's influence, and its ripple effects on star formation, planetary development, and the delicate conditions required for life to emerge and thrive. Our galaxy, the Milky Way, is a sprawling spiral of hundreds of billions of stars, vast molecular clouds, and intricate cosmic structures, all interconnected by gravitational forces and enriched by cycles of stellar birth and death. Within this vast expanse, certain regions teem with the ingredients for life: dense molecular clouds filled with complex organic molecules, young stars with stable planetary systems, and environments shielded from the most violent cosmic events. However, the arrival or presence of a hypermagnetar would shatter this delicate equilibrium. Imagine a sphere of influence around a hypermagnetar, a dead zone, that extends for many light years in every direction, where the star's magnetic field obliterates molecules, tears apart atoms, and fries the delicate chemistry essential for life. This invisible yet omnipresent force acts like a cosmic sterilizer, sweeping through interstellar space and preventing the formation of new stars and planets within its reach. Any nascent star system attempting to emerge in this zone would find itself unable to hold onto its atmosphere or retain the molecular complexity necessary for life-supporting environments. Within this hazardous bubble, the molecular clouds that serve as stellar nurseries would be disrupted or dispersed. The intense radiation and magnetic forces would ionize gases, destroy dust grains, and prevent the gravitational collapse of clouds into protostars. This suppression of star formation would create barren patches within the galaxy, regions where the natural recycling of matter into new celestial bodies grinds to a halt. Beyond the inhibition of star formation, existing planetary systems within this range would be subjected to relentless bombardment by gamma-ray bursts, high-energy particles, and electromagnetic storms emanating from the hypermagnetar. The intense radiation would strip atmospheres from planets, break down protective ozone layers, and irradiate any surface life, making habitability virtually impossible. Even subsurface or deep oceanic life forms would face threats from penetrating radiation and energetic particle fluxes. Moreover, the gravitational disturbances caused by the hypermagnetar could destabilize orbits within affected systems, exposing planets to extreme climate swings or ejecting them into the cold darkness of interstellar space. The magnetic field's interactions with stellar winds and magnetic cycles would trigger unpredictable and violent stellar activity, further exacerbating the hostile conditions. The size of this galactic hazard would depend on the hypermagnetar's properties, its magnetic field strength, rotation rate, and age, but even a conservative estimate suggests a radius of influence spanning tens of light years, encompassing volumes of space containing thousands or even millions of stars. Within this zone, life as we understand it would be not just endangered but effectively impossible. This raises profound implications for the distribution of life in the galaxy. The hypermagnetar's presence would carve out dead zones, devoid of life and star formation, shaping the galactic ecology in ways that go beyond gravitational dynamics and elemental enrichment. These sterilized regions could act as barriers, isolating pockets of habitable space and influencing the migration and evolution of life-bearing systems. From an observational standpoint, astronomers might detect these galactic hazards through anomalies in star formation rates, unusual patterns in chemical abundances, or the presence of high-energy emissions without clear sources. Such indicators could guide searches for hidden hypermagnetars lurking in the shadows, whose destructive spheres have long gone unnoticed. Furthermore, the existence of even a single hypermagnetar in the Milky Way challenges assumptions about the galaxy's habitability and the resilience of life. It underscores the fragility of cosmic neighborhoods and the precariousness of the conditions that allowed Earth, and potentially other worlds, to harbor life. In the grand tapestry of the Milky Way, a hypermagnetar would be a cosmic blemish, a scar of destruction that interrupts the natural flow of creation and evolution. It serves as a reminder that the galaxy is not a uniformly benign environment, but a dynamic, often violent place where the forces of death and renewal coexist in delicate balance. Ultimately, the galactic hazard posed by a hypermagnetar highlights the need for vigilance and continued exploration. Understanding these deadly stars helps us appreciate the fragility of life's cosmic cradle and the extraordinary circumstances that make our existence possible. It also fuels the search for cosmic phenomena that, while invisible and distant, wield the power to reshape entire regions of the universe, silently guarding the boundary between creation and annihilation. The question naturally arises: if hypermagnetars are so extraordinarily powerful and dangerous, why have we never observed one directly? Why does this cosmic monster remain purely theoretical, a specter lurking in astrophysicists' equations and simulations but absent from our telescopic surveys? Understanding the reasons for their apparent invisibility is crucial not only for grasping the nature of hypermagnetars but also for appreciating the limits of our observational capabilities and the challenges posed by extreme astrophysical phenomena. One plausible scientific explanation lies in their sheer rarity. Hypermagnetars, by definition, require an extraordinary set of conditions to form, far beyond those needed to create ordinary neutron stars or even magnetars. The birth of a hypermagnetar likely demands a hypernova event of staggering magnitude, involving the collapse of a supermassive star with a mass perhaps tens of times greater than that which produces typical magnetars. This catastrophic collapse would need to channel an unimaginable amount of energy into a tiny remnant, while simultaneously generating a magnetic field a trillion times stronger than those observed in known magnetars. Given the extreme fine-tuning involved, such stars might be extraordinarily rare, perhaps forming only once every millions or even billions of years within a typical galaxy. Their scarcity alone could explain why we have yet to detect one directly. Another factor is their lifespan, or rather, their potential lack thereof. The magnetic fields of hypermagnetars, so intense as to distort atomic structures and create spheres of annihilation across light years, may also be inherently unstable. The energy stored in such colossal magnetic fields would likely dissipate quickly, via bursts of electromagnetic radiation, magnetic reconnection events, and particle acceleration. This rapid decay could limit the hypermagnetar's lifetime to perhaps thousands or tens of thousands of years, a blink of an eye on cosmic timescales. If these stars exist only fleetingly, the window during which we might observe one is extraordinarily narrow. By the time we point our most powerful instruments in the right direction, the hypermagnetar may have already faded into a more stable, less extreme neutron star, or collapsed further into a black hole, effectively ending its reign of terror. Furthermore, the extreme danger posed by hypermagnetars may also contribute to their invisibility. Their colossal magnetic fields and intense radiation could sterilize or destroy any matter in their vicinity, including the accretion disks or companion stars that often serve as bright beacons around compact objects. Without a surrounding disk of infalling matter to generate X-rays or gamma rays, a hypermagnetar might emit little detectable radiation in steady states, making it effectively dark, except during rare, brief flare events. Such transient emissions could be easily missed by surveys not tuned to detect fleeting high-energy bursts. The hypermagnetar's invisibility is compounded by the fact that it might reside deep within dense molecular clouds or regions of intense interstellar dust. These cosmic veils absorb visible light and many forms of radiation, obscuring objects from telescopes that rely on traditional wavelengths. Only instruments capable of detecting radio waves, X-rays, or gamma rays might penetrate these barriers, and even then, the signals could be faint or confused with other high-energy astrophysical phenomena such as gamma-ray bursts or pulsar wind nebulae. The hypermagnetar's rarity and transient nature, combined with its possible obscuration by interstellar matter, create a perfect storm of observational challenges. Additionally, the hypermagnetar might be confused with other exotic objects. Its intense magnetic field and rapid rotation could produce pulsar-like signals, but with unusual characteristics. Distinguishing a hypermagnetar from a regular magnetar or a pulsar requires detailed, high-resolution observations over extended periods, a resource-intensive task. As a result, potential hypermagnetar candidates may remain unidentified or misclassified within existing catalogs. Theoretical models also suggest that hypermagnetars could evolve rapidly into other compact objects, such as black holes or quark stars, further limiting their detectability. Their extreme magnetic and gravitational pressures might trigger phase transitions in their dense cores, causing changes that mask their true nature. This evolutionary path complicates efforts to identify hypermagnetars, as the objects we observe might represent only the end stages of their brief existence. From a cosmological perspective, hypermagnetars might have been more common in the early universe, during epochs of intense star formation and greater abundance of massive stars. However, their remnants could have long since faded or collapsed, leaving behind only indirect evidence. This historical scarcity in the current epoch would explain their absence from modern surveys while preserving their role in shaping the chemical and structural evolution of galaxies. In sum, the reasons we have never seen a hypermagnetar directly likely include a combination of rarity, short lifespan, obscuration by interstellar matter, and the intrinsic difficulty of distinguishing their signals from other high-energy astrophysical sources. These factors converge to shroud the hypermagnetar in mystery, making it one of the universe's most elusive and enigmatic phenomena. Yet, this invisibility does not imply insignificance. On the contrary, the mere theoretical possibility of such a star challenges astronomers to push the boundaries of observation and theory. It drives the development of more sensitive instruments, new data analysis techniques, and deeper surveys of the high-energy universe. It invites speculation about hidden dangers lurking in the cosmic shadows and underscores the need for vigilance in monitoring the skies for signs of these silent but deadly titans. As our technology advances, the veil may lift, and one day, we may glimpse a hypermagnetar in all its terrifying glory, an ephemeral beacon of destruction whose presence forces us to rethink the limits of stellar physics and the precarious balance of life in the cosmos. Until then, the hypermagnetar remains a ghostly possibility, a cosmic monster waiting just beyond the edge of our sight. The search for a hidden hypermagnetar, an astrophysical behemoth with a magnetic field trillions of times stronger than anything yet observed, poses one of the most tantalizing challenges in modern astronomy. Because these objects might lurk unseen, cloaked in darkness or obscured by interstellar matter, astronomers must rely on indirect clues, subtle signatures etched in the light and radiation streaming from surrounding regions, to infer their presence. Detecting these signs requires a combination of theoretical insight, cutting-edge instrumentation, and careful analysis of anomalies in data that at first might seem unrelated or puzzling. One of the primary signatures astronomers might detect from a hypermagnetar is the distortion of light emanating from nearby stars and gas clouds. Unlike typical stars, whose light travels largely unimpeded across space, the extreme magnetic fields and intense radiation from a hypermagnetar could alter the properties of photons passing near it. This effect, known as vacuum birefringence, occurs when a strong magnetic field causes the vacuum of space itself to act like a prism, splitting and polarizing light in unusual ways. Observing polarized light, or anomalies in stellar spectra could reveal the presence of magnetic fields far beyond the normal range, pointing to a hypermagnetar lurking nearby. In addition, the gravitational influence of a hypermagnetar could subtly warp the paths of light rays from distant stars, producing minute but detectable distortions in their apparent positions or brightness. Such gravitational lensing effects, though typically associated with massive objects like black holes or galaxies, might also arise in smaller but intensely magnetic environments due to the complex interplay of gravity and magnetism. Detecting these minute shifts requires high-precision astrometry, such as that conducted by the Gaia Space Observatory, which measures stellar positions with unprecedented accuracy. Unexplained deviations or systematic patterns in stellar motion or brightness could hint at the gravitational signature of a hidden hypermagnetar. Another hallmark would be the detection of unusual gamma-ray bursts, GRBs, or transient high-energy flares emanating from seemingly empty regions of space. Hypermagnetars are theorized to produce sporadic bursts of electromagnetic energy, far more powerful and distinct than those from typical magnetars or pulsars. Unlike classical GRBs, which usually result from catastrophic events like supernovae or neutron star mergers and last from milliseconds to minutes, hypermagnetar bursts might have unique temporal profiles, energy spectra, or polarization properties that set them apart. Astronomers analyzing data from satellites like NASA's Fermi Gamma-Ray Space Telescope or the European Space Agency's Integral Observatory look for such peculiar bursts that do not fit existing classifications. Closely linked to gamma-ray emissions are the accompanying radio waves, X-rays, and neutrinos produced by particle acceleration in the hypermagnetar's magnetosphere. Multi-wavelength observations become crucial, as coordinated detection of signals across the electromagnetic spectrum strengthens the case for a hypermagnetar. For example, A sudden gamma-ray flare followed by a delayed radio afterglow with unusual polarization might be a smoking gun. Detecting neutrinos, ghostly particles that rarely interact with matter, would add further confirmation, as hypermagnetar bursts could produce copious neutrinos through nuclear interactions in their magnetospheres. Space anomalies beyond just electromagnetic signatures might also betray a hidden hypermagnetar. Astronomers could detect gaps or distortions in molecular clouds or stellar nurseries, regions where star formation suddenly halts or is disrupted without obvious cause. These dead zones could indicate the presence of an intense magnetic or radiation field preventing the collapse of gas into new stars. Similarly, unusually ionized gas or strange chemical abundances in interstellar clouds might be traced back to the irradiation or magnetization caused by a hypermagnetar's influence. A further subtle clue comes from changes in the dynamics of nearby stellar systems. If stars in a cluster or neighborhood exhibit unusual orbital perturbations, unexplained acceleration, or rapid spin changes, it might reflect gravitational and magnetic disturbances from a hidden hypermagnetar. Precise measurements of stellar velocities, rotations, and magnetic field strengths, combined with computer simulations, help identify these anomalies. Such perturbations might also produce heightened rates of stellar collisions or mergers, further betraying the unseen hand of the hypermagnetar. Another promising avenue is the search for persistent, localized sources of intense magnetic fields. Some neutron stars, classified as magnetars, show magnetic fields on the order of 10 to the power of 14 to 10 to the power of 15 Gauss. If astronomers detect objects with even stronger magnetic signatures, approaching or surpassing these magnitudes, it would be an indicator of hypermagnetar candidates. However, measuring magnetic fields of distant stars is challenging, often requiring indirect methods such as analyzing spectral line splitting, Zeeman effect, or studying magnetospheric emission properties. Beyond individual observations, astronomers can search for statistical anomalies in large datasets. For example, regions with unexpectedly high rates of high-energy transit events, or areas where star formation is inexplicably suppressed, may hint at the presence of a hypermagnetar. Cross-referencing catalogs of gamma-ray bursts, radio pulsars, and X-ray sources against molecular cloud maps and star formation rates can reveal suspicious correlations worthy of follow-up study. The challenge in identifying hypermagnetars is compounded by their potential variability. These stars might be quiet most of the time, emitting little radiation, and suddenly erupt in violent flares or bursts. This episodic behavior means that many transient surveys could miss them unless monitoring is continuous and sensitive across multiple wavelengths. Dedicated observation campaigns, using networks of telescopes around the world and in space, increase the chances of catching these rare events. Technological advancements in telescope sensitivity, resolution, and multi-messenger astronomy, where electromagnetic signals are combined with neutrino and gravitational wave detections, are opening new frontiers in the hunt. Although gravitational waves from hypermagnetars are expected to be weak compared to black hole mergers, any detection of anomalous gravitational signals correlated with high-energy bursts could provide a new tool for discovery. Another speculative sign might be the detection of peculiar cosmic rays or high-energy particles with unusual composition or energy spectra, accelerated by the intense magnetic fields near a hypermagnetar. Such particles could reach Earth and be captured by detectors like the Pierre Auger Observatory, offering indirect evidence of the star's violent processes. In summary, the signs of a hidden hypermagnetar are subtle, complex, and multifaceted. Astronomers look for distorted light patterns, unusual gamma-ray bursts, space anomalies in molecular clouds, and gravitational or magnetic disturbances in nearby stars. They rely on coordinated multi-wavelength and multi-messenger observations, detailed simulations, and the continuous refinement of theoretical models to distinguish these signals from the cosmic noise. While no definitive hypermagnetar has yet been identified, the search itself pushes the boundaries of astrophysics and deepens our understanding of the most extreme environments in the universe. Each anomalous signal or unexplained burst brings us a step closer to unveiling these silent but devastating cosmic predators, lurking in the shadows and silently shaping the cosmos with their invisible but overwhelming power. The idea that a hypermagnetar could already be heading toward our solar system, even from many light years away, is a chilling and humbling prospect, one that confronts us with the vast scales and powerful forces of the universe, and the fragile bubble of life that Earth occupies within it. Though hypermagnetars remain purely hypothetical, the very possibility of their existence raises urgent questions. Could such a cosmic monster be lurking unseen in the dark stretches of our galaxy? And if so, what would it mean if it were on a collision course with our neighborhood? To explore this unsettling scenario, we must first understand the nature of cosmic distances, stellar motion, and the potential warning signs and limitations of detecting such an approaching threat. The Milky Way galaxy, a sprawling spiral of hundreds of billions of stars, stretches approximately 100,000 light-years in diameter. Stars and stellar remnants orbit the galactic center at various speeds and trajectories, influenced by the gravity of the galaxy's mass distribution, as well as local interactions with nearby objects. Over millions of years, stars drift, encounter, and occasionally collide with one another, though such events are rare on human timescales. For a hypermagnetar, born from the collapse of a massive progenitor star, likely in a hypernova explosion, its initial velocity might be significant, potentially propelled by asymmetric forces during its formation, known as kick velocities. These kicks can send neutron stars hurtling through space at hundreds, or even thousands of kilometers per second, making them wanderers in the galactic sea. Given this, a hypermagnetar formed tens or hundreds of light-years away could be moving toward the solar system, albeit on a timescale measured in thousands to millions of years. Even at vast distances, the hypermagnetar's extraordinary magnetic field and associated electromagnetic radiation could begin affecting space far beyond its physical position. The reach of its magnetic field could extend light-years, subtly altering the cosmic environment and potentially signaling its presence long before it arrives close enough to cause catastrophic effects locally. The prospect of a hypermagnetar approaching raises immediate concerns about detectability. Despite advances in astronomical observation, identifying such an object at great distances is challenging. Its potential invisibility, due to lack of steady emission and possible obscuration by dust clouds, means it might travel through the galaxy largely unnoticed until it reaches the outer fringes of the solar system or beyond. By the time its effects are detected, warning times could be alarmingly short. Astronomers rely on indirect signs, unexplained bursts of gamma rays, distortions in the trajectories of nearby stars, anomalies in the interstellar medium, and unusual cosmic ray fluxes. Yet these clues require careful interpretation, and in many cases, could be dismissed as noise or attributed to more mundane phenomena. A hypermagnetar moving steadily toward us might masquerade as an unremarkable neutron star or remain entirely undetected due to its transient nature. As it closes in, the hypermagnetar's magnetic field would begin to interact with the heliosphere, the protective magnetic bubble created by the sun that shields the solar system from cosmic radiation. Disturbances in the heliosphere might manifest as fluctuations in cosmic ray intensity, shifts in solar wind properties, or unexplained magnetic anomalies detected by spacecraft such as Voyager or the Parker Solar Probe. These subtle effects could serve as early warnings, but interpreting them correctly would require a deep understanding of the hypermagnetar's properties and its spatial relationship to the solar system. If the hypermagnetar continued its approach, the destructive radius, where its magnetic field strips atoms apart, disrupts molecular bonds, and bathes the environment in lethal radiation, would begin encroaching on the outer planets and eventually Earth itself. Within this kill radius, life as we know it would be impossible to sustain. Satellites and spacecraft would fail as their electronics fried, atmospheric chemistry would be disrupted, and surface life would face extinction-level events. The vastness of space and the relative slowness of cosmic motion provide some reassurance. Any hypermagnetar on a direct collision course with Earth would likely take thousands of years to arrive, offering theoretical time to study and potentially develop countermeasures, though such technology remains firmly in the realm of speculation. However, the unpredictability of hypermagnetar formation and movement means we must remain vigilant, continually scanning the skies and refining models of stellar evolution and galactic dynamics. This possibility also prompts philosophical reflection on humanity's place in the cosmos. It underscores how our existence is contingent not only on local planetary conditions but also on the broader cosmic environment. The unseen forces shaping the galaxy could, in a heartbeat, alter the trajectory of life on Earth. In conclusion, while there is currently no evidence of a hypermagnetar heading toward us, the theoretical possibility is real enough to inspire both awe and caution. The universe is vast, full of mysteries and dangers that transcend human timescales and perceptions. Preparing for such a cosmic threat begins with understanding, observation, and the relentless pursuit of knowledge, tools that may one day protect us from the silent approach of the star that ends worlds. The terrifying reality of a hypermagnetar's approach is that escape from its deadly influence might be fundamentally impossible. Unlike many cosmic threats, such as asteroids, comets, or rogue planets, that could theoretically be detected early and deflected or avoided, the hypermagnetar represents a class of cosmic menace for which the very concept of escape or evasion may be meaningless. By the time humanity or any advanced civilization could even detect its presence, the lethal effects of its magnetic field and radiation would already be well underway, sealing the fate of anything within its sphere of influence. To understand why escape is impossible, we must first grasp the extraordinary nature of the hypermagnetars. Kill radius. This zone is not a conventional boundary like the event horizon of a black hole, where matter crosses a point of no return. Instead, it is an immense, invisible sphere defined by the sheer strength and reach of its magnetic field and radiation. This sphere can extend across many light years, enveloping entire star systems and molecular clouds, tearing apart atoms and molecules simply by proximity. Because the hypermagnetar's destructive influence radiates outward at the speed of light, its reach precedes any physical movement of the star itself, meaning the threat expands even before the star approaches physically. When astronomers finally detect signs of a hypermagnetar, whether through unusual gamma-ray bursts, unexpected distortions in stellar orbits, or anomalous electromagnetic phenomena, the star may already be well within a dangerous proximity. This means the detection window between first observation and unavoidable destruction could be incredibly short on cosmic scales, potentially years or decades at best. Given the immense distances involved, the warning time would be too brief to implement any meaningful planetary defense or evacuation strategy. Unlike asteroids, which move relatively slowly and can be tracked for decades or centuries before a potential impact, the hypermagnetar's destructive effects do not require a direct collision or close approach. Its magnetic field and radiation ripple through space, interacting with matter and energy across vast distances, making traditional concepts of trajectory and avoidance inadequate. Even if the star itself is hundreds or thousands of light years away, its influence could be altering the interstellar environment and jeopardizing life in ways that cannot be mitigated. Moreover, the physical means of escape, leaving the solar system, moving to distant star systems, or shielding against the radiation, pose enormous technological challenges. Human space exploration, while advancing rapidly, remains confined primarily to Earth orbit and the inner solar system. The idea of evacuating an entire planet or civilization is currently beyond our reach. Even if a fraction of humanity were to venture into space habitats or other planets, the sheer scale of the hypermagnetar's kill radius could encompass entire solar systems, rendering such refuges unsafe. Shielding against the hypermagnetar's magnetic field and radiation also stretches current scientific understanding and engineering capabilities. Magnetic fields strong enough to distort atoms themselves would overwhelm any conceivable human-made shield or electromagnetic barrier. Radiation levels equivalent to or exceeding gamma-ray bursts would penetrate conventional materials and electronics, causing widespread damage. The ionizing radiation alone would sterilize environments, break down biological molecules, and disrupt electronic systems vital for survival. This lethal environment extends beyond physical effects. The hypermagnetar's radiation could disrupt planetary atmospheres, altering climate and chemistry irreversibly. Ozone layers could be stripped away, exposing the surface to deadly ultraviolet radiation. The bombardment of charged particles would create global electrical storms, damaging infrastructure and potentially triggering cascading ecological collapse. The fundamental nature of the hypermagnetar also challenges our ability to predict or prepare for its effects. The magnetic field's strength and variability could produce sudden flares or bursts that compound the danger unpredictably. Unlike a predictable asteroid impact or supernova explosion, the hypermagnetar's behavior might be erratic, with periods of relative quiet punctuated by devastating eruptions of energy. Even if early detection technologies were to improve dramatically, allowing astronomers to identify hypermagnetars at greater distances or earlier in their life cycles, the intrinsic properties of these stars would limit our options. The propagation of electromagnetic effects at light speed means the damage front arrives as fast as information about it, leaving no practical time for intervention once effects are measurable near Earth. In this sense, the hypermagnetar embodies a cosmic noose, an inescapable fate for any object or life form caught within its reach. It stands in stark contrast to other cosmic dangers where human ingenuity and technology might offer solutions or mitigations. The hypermagnetar's threat is absolute, silent, and all-encompassing. This harsh truth has profound implications for our understanding of cosmic safety and the resilience of life in the universe. It serves as a sobering reminder that despite humanity's advances, we remain vulnerable to forces far beyond our control, governed by the laws of physics and the vast scales of space and time. The universe harbors hidden predators that do not announce their presence until it is too late, and the hypermagnetar is perhaps the most extreme example. Philosophically, the inevitability of the hypermagnetar's destructive reach challenges the notion of cosmic security. It emphasizes the precariousness of existence, not only on Earth but across the galaxy. It compels us to deepen our commitment to space observation, theoretical research, and the search for advanced civilizations that might possess knowledge or technology to detect and survive such threats. In conclusion, escape from a hypermagnetar's deadly influence is not merely difficult, it is likely impossible once the star's presence is known. Its vast kill radius, speed of destructive effects, and overwhelming physical power mean that by the time humanity or any other civilization detects the threat, the catastrophic consequences are already unfolding. The hypermagnetar stands as a stark symbol of cosmic inevitability and the ultimate limits of survival in an unforgiving universe. The concept of a hypermagnetar, a star wielding magnetic fields a trillion times stronger than any known magnetar, pushes the very boundaries of our current understanding of physics. If such an object exists, it would not only be the most dangerous star in the universe but also a cosmic enigma that challenges the fundamental laws that have guided science for centuries. Exploring how the existence of a hypermagnetar could force scientists to rewrite or drastically revise major laws of physics reveals just how revolutionary this hypothetical star truly is. At the heart of the issue lies the unprecedented strength of the hypermagnetar's magnetic field. Typical magnetars already boast magnetic fields on the order of 10 to the power of 14 to 10 to the power of 15 Gauss, which themselves defy many classical models of stellar behavior. These intense fields already influence matter and spacetime in ways that require relativistic and quantum corrections to explain. However, a hypermagnetar's magnetic field, theorized to be a trillion times stronger than even these extremes, would enter a regime where current theories may no longer apply or must be fundamentally extended. One key area that would come under scrutiny is quantum electrodynamics, QED, the theory describing how light and matter interact, and the behavior of electromagnetic fields at the quantum level. In fields of the strength predicted for hypermagnetars, vacuum polarization effects become significant to an extreme degree. The vacuum itself behaves like a nonlinear medium, where photons can interact and even split, phenomena that are only faintly observed around magnetars today. The hypermagnetar's environment could reveal new quantum states of the vacuum, forcing physicists to develop more complete theories that can accurately describe these extreme conditions. Moreover, the distortion of atomic and subatomic particles by such a field would push particle physics into unexplored territory. The electrons, protons, and neutrons in atoms near a hypermagnetar would experience forces so strong that their standard behavior changes drastically. Particles might exhibit altered magnetic moments, masses, or decay rates under such influence. Detecting and modeling these effects could provide insights into the strong and weak nuclear forces in ways currently impossible, leading to revisions in the standard model of particle physics. The star's magnetic field could also affect the structure of the neutron star itself, challenging models of neutron degeneracy pressure, the force preventing collapse in neutron stars. If the magnetic pressure exceeds gravitational pressure locally or globally within the star, it might create exotic phases of matter, such as quark-gluon plasma or even hypothetical states like color superconductors, requiring new equations of state. Understanding these phases would deepen knowledge of nuclear physics and the behavior of matter at densities beyond those achievable in Earth-based laboratories. General relativity, the theory describing gravity as the curvature of spacetime, may also face challenges from the hypermagnetars conditions. While gravity dominates large-scale cosmic phenomena, the interplay of immense magnetic fields with curved spacetime could produce novel effects. The coupling between electromagnetic fields and gravity might need to be revised or extended through alternative theories of gravity or quantum gravity models. The intense magnetism could induce anisotropies or instabilities in spacetime around the star, perhaps affecting gravitational wave signatures or the star's collapse dynamics. One of the most profound implications relates to the limits of magnetic field strength itself. Classical physics predicts a maximum magnetic field intensity before the vacuum breaks down and matter cannot exist in familiar forms. The hypermagnetar, by existing beyond this threshold, could reveal new physics beyond the magnetic Eddington limit, analogous to the radiation pressure limit for luminosity. Such discoveries could open pathways to understanding fundamental constants, symmetry breaking, and the unification of forces. The behavior of light in the hypermagnetar's vicinity would also prompt revisions in optics and astrophysics. Photon splitting, pair production, creation of electron-positron pairs, and other nonlinear QED effects might be commonplace. Light propagation could become dispersive or directional in unexpected ways, influencing the interpretation of astronomical observations and the nature of cosmic backgrounds. Additionally, the hypermagnetar's violent bursts of gamma rays and other high-energy phenomena might illuminate processes related to cosmic ray acceleration, plasma physics, and magnetic reconnection on scales never before seen. Understanding these processes could improve models of space weather, magnetospheric physics, and particle astrophysics. Theoretical physics may need to incorporate the hypermagnetar's conditions into unified theories attempting to reconcile quantum mechanics and general relativity. Such extreme environments serve as natural laboratories for probing quantum gravity, string theory, or loop quantum gravity, potentially guiding breakthroughs that have eluded physicists for decades. In essence, the hypermagnetar sits at the intersection of multiple fields: quantum physics, astrophysics, nuclear physics, relativity, and cosmology, each challenged by its extreme properties. Its existence would demand new mathematical frameworks, revised physical constants, and innovative experimental approaches. The star would become a touchstone for fundamental physics, inspiring generations of scientists to explore the universe's most extreme frontiers. In summary, the hypermagnetar represents not just a cosmic predator but a catalyst for scientific revolution. By pushing the boundaries of magnetic field strength, matter stability, and space-time behavior, it threatens to overturn established paradigms and open new vistas of understanding. The star that ends worlds might also be the star that begins a new era in physics. The cosmic landscape is peppered with extraordinarily lethal phenomena. Black holes and hypermagnetars rank among the most fearsome. Both represent the extreme endpoints of stellar evolution and are capable of obliterating anything that ventures too close. Yet, their modes of destruction are fundamentally different. Comparing their lethality offers profound insights not only into the nature of these enigmatic objects, but also into the diversity of cosmic threats that shape the universe. Here, we delve deep into the distinctions and similarities between black holes and hypermagnetars, focusing on how each claims its victims and the broader implications for life and matter across the cosmos. Black holes are regions of spacetime where gravity reigns supreme, so intense that nothing, not even light, can escape once it crosses the event horizon. Their lethality stems from this inescapable gravitational pull, which crushes matter into a singularity, a point of infinite density where the known laws of physics break down. Black holes come in various sizes, from stellar mass black holes formed by the collapse of massive stars, to supermassive black holes anchoring galaxies. Their ability to consume matter and warp spacetime around them makes them some of the most feared cosmic entities. In contrast, hypermagnetars are neutron stars with magnetic fields trillions of times stronger than any known magnetar, fields so powerful they distort and tear apart matter at the atomic level across light years. Unlike black holes, which rely on gravity's crushing power, hypermagnetars exert their lethal influence primarily through electromagnetic forces. Their magnetic fields can rip electrons from nuclei, destroy molecules, and generate intense bursts of gamma radiation that sterilize entire star systems. The hypermagnetar's kill radius extends far beyond its physical size, making it a silent but all-encompassing predator. The lethality of black holes is localized but absolute. Once matter crosses the event horizon, it is doomed to inexorable collapse. The gravitational tidal forces near smaller black holes can spaghettify objects, stretching them into long, thin shapes before final consumption. For supermassive black holes, the tidal forces at the event horizon can be less immediately destructive, but the gravitational trap remains fatal. Black holes can also influence their environments by accreting gas, emitting jets of high-energy particles, and distorting light paths, phenomena that shape galactic evolution. Hypermagnetars, on the other hand, extend their lethal influence over a vast volume of space. Their magnetic fields are not confined to a horizon but permeate the surrounding region, disrupting atomic and molecular structures even without direct contact. This means destruction begins well before anything physically approaches the star. Unlike black holes, hypermagnetars can sterilize regions of space by electromagnetic force alone, affecting planets, spacecraft, and interstellar matter alike. From a survival standpoint, approaching a black hole is fatal because of gravitational capture and eventual spaghettification. Approaching a hypermagnetar is equally fatal but for different reasons. The magnetic field and radiation would destroy matter before gravitational forces could act. In fact, the hypermagnetar's gravitational pull, while strong, is typically less immediately destructive than its magnetism. This is a stark contrast to black holes, where gravity is the sole lethal agent. Black holes can be hidden in darkness, invisible unless surrounded by glowing accretion disks or causing gravitational lensing. Hypermagnetars may also be invisible, cloaked by dust or faint invisible light, but their powerful magnetic and radiation signatures can betray them. The detection of gamma-ray bursts or anomalous electromagnetic phenomena often leads astronomers to magnetars or neutron stars, while black holes are identified through X-ray emissions and their gravitational effects on nearby objects. The timescales of destruction differ. Black holes consume matter gradually. Accretion disks and jets operate over millions of years, though the infall across the event horizon is rapid once matter crosses the point of no return. Hypermagnetars can emit sudden bursts of gamma radiation, flares that last seconds to minutes but can sterilize vast regions instantaneously. This episodic lethality makes hypermagnetars unpredictable and terrifying. In terms of reach, a black hole's lethal boundary is defined by the event horizon. Beyond this boundary, matter is safe. For a hypermagnetar, there is no such horizon. Its magnetic influence extends light years, making the kill radius potentially thousands of times larger than the star's physical size. This enormous zone of influence transforms the hypermagnetar into a silent cosmic predator, killing from afar without the need to capture or consume. Energy output mechanisms differ fundamentally. Black holes release energy through gravitational processes. Matter spiraling into the black hole releases gravitational potential energy, converting it into electromagnetic radiation and relativistic jets. Hypermagnetars release energy stored in their magnetic fields, which can be suddenly unleashed in gamma-ray flares. These flares can be among the most energetic events in the universe, rivaling supernova explosions in their intensity. The impact on life and planetary systems varies accordingly. A planet caught near a black hole risks being torn apart by tidal forces or swallowed whole, but a system several light-years away might remain unaffected. Conversely, a hypermagnetar's magnetic field can sterilize planets at vast distances, stripping atmospheres, disrupting chemistry, and irradiating surfaces without direct gravitational interaction. Thus, hypermagnetars pose a more pervasive threat to life over wider spatial scales. From a cosmological perspective, black holes play critical roles in galaxy formation and evolution. Supermassive black holes regulate star formation and influence galactic dynamics through feedback mechanisms. Hypermagnetars, if they exist, could also shape their environments by sterilizing regions, preventing star formation, or influencing interstellar chemistry, but their role is less understood due to their hypothetical nature. Both objects challenge fundamental physics but in different ways. Black holes embody the extreme of gravitational physics and space-time curvature, leading to singularities and event horizons that push the limits of general relativity. Hypermagnetars push electromagnetic and quantum theories to their limits, potentially revealing new physics and ultra-strong magnetic fields in dense matter. Technologically, encountering a black hole would mean crossing an invisible point of no return, while approaching a hypermagnetar would cause immediate system failures and radiation damage long before any close approach. For spacefaring civilizations, the hypermagnetar represents a hazard that can disable spacecraft remotely, making evasion or defense exceedingly difficult. In terms of detectability, black holes can be inferred by their gravitational effects on stars and gas or by X-ray emissions from accretion disks. Hypermagnetars may reveal themselves through bursts of gamma rays, polarized radiation, or disturbances in nearby interstellar matter. Both require sophisticated instruments and multi-wavelength observations to identify and characterize. Ultimately, both black holes and hypermagnetars represent cosmic endpoints of stellar death and destruction, but their methods diverge sharply. Black holes kill by gravity's inescapable pull, crushing matter into oblivion, while hypermagnetars kill by sheer magnetic destruction, unbinding matter at the atomic level from vast distances. The contrast highlights the diverse and extreme mechanisms the universe employs to shape and sometimes annihilate matter and life. In conclusion, the hypermagnetar stands as a unique and terrifying addition to the pantheon of cosmic killers, complementing black holes with a different kind of lethality that extends its reach invisibly across space. Understanding and comparing these phenomena enriches our appreciation of the universe's power and complexity, and underscores the precariousness of life amid such overwhelming forces. The universe is vast, beautiful, and endlessly mysterious, but it is also filled with hidden killers. These are cosmic threats so silent, so subtle, that you might never know they are there until it is already too late. They lurk in the dark spaces between stars, in the shadows of galaxies, or cloaked by the very physics that govern existence. Among these silent killers, the hypermagnetar ranks as one of the most insidious and devastating. Its power lies not in spectacle, but in invisibility and inevitability, qualities that define many of the deadliest cosmic phenomena. Unlike cataclysmic supernovae whose explosive light floods the cosmos, or black holes whose gravitational grip warps space itself, silent killers do not advertise their presence. They do not emit brilliant flares visible across galaxies, nor do they necessarily consume matter in dramatic ways. Instead, they exert their influence through unseen forces, subtle distortions, or radiation that travels invisibly through the vastness of space, leaving destruction in their wake before a single photon of warning can reach potential victims. The hypermagnetar epitomizes this deadly stealth. With a magnetic field potentially 1 trillion times stronger than the strongest magnetars we know, its lethal zone extends across light years, shredding atoms and destabilizing molecules far beyond its physical boundaries. Yet, it may appear as just another faint, dim point of light, or even be completely invisible, until its magnetic death radius reaches unsuspecting systems. This invisibility makes it far more dangerous than any obvious cosmic explosion. A civilization could go about its existence, oblivious to the invisible threat silently unraveling its very molecular foundations. Silent killers like hypermagnetars challenge our perception of safety in the cosmos. The sheer emptiness of space is deceptive. It might lull us into a false sense of security. But hidden within that emptiness could be pockets of lethal radiation, intense magnetic fields, or exotic particles that wreak havoc silently. These dangers evade early detection because they do not rely on direct physical impact or explosive signatures. Instead, their destructive reach comes from subtle, pervasive forces operating on scales and through mechanisms that current technology can barely detect. Beyond hypermagnetars, the universe hides many such threats. Cosmic rays, high-energy particles traveling near light speed, bombard planets constantly but are mostly deflected by magnetic fields. However, bursts of cosmic rays from distant gamma-ray bursts or magnetar flares could sterilize entire biospheres if directed their way. Rogue black holes, drifting silently through interstellar space, can pass undetected for eons, only revealing themselves through gravitational disturbances or the destruction of nearby systems long after their arrival. Dark matter clumps, though invisible and poorly understood, could gravitationally disrupt star orbits, leading to catastrophic chain reactions. Other silent cosmic killers include the so-called blitzer stars, neutron stars that collapse suddenly into black holes, emitting gamma-ray bursts without warning, or fast radio bursts, mysterious millisecond pulses of energy that might herald exotic astrophysical events we have yet to comprehend fully. The cosmic microwave background radiation itself, a faint echo of the Big Bang, carries subtle irregularities that may hint at large-scale hidden structures or threats. What ties all these silent killers together is their ability to hide in plain sight, masked by the vastness of space and the limits of human perception. Their detection often requires complex, multi-wavelength astronomy, involving gamma rays, X-rays, gravitational waves, neutrinos, and other exotic messengers. Even with our most advanced telescopes and detectors, many silent killers remain elusive, known only through indirect evidence or theoretical predictions. The existential risk posed by such silent cosmic killers is profound. Unlike localized disasters on Earth, these threats operate on scales that can wipe out entire planetary systems or sterilize swaths of the galaxy. For any intelligent life form, the danger is not just physical annihilation but also the abrupt end to evolution and potential survival, often without any chance for warning or escape. The hypermagnetar's particular mode of destruction, tearing apart matter from across light years using magnetic fields and gamma radiation, exemplifies this silent menace. Its influence does not require proximity or collision, unlike meteor impacts or supernova shockwaves. Instead, it kills remotely, invisibly, making it a predator that hunts through space without movement or noise. This raises unsettling questions about the prevalence of life in the universe. Could such silent killers be a reason why we have not yet encountered other civilizations, a cosmic filter that extinguishes life before it can spread? Are our observations skewed by the invisibility of these threats, making the universe appear more hospitable than it really is? In response, scientists strive to improve detection methods. Advances in gamma-ray astronomy, gravitational wave observatories, neutrino detectors, and cosmic ray monitoring all aim to uncover these silent killers before they strike. Projects like the Fermi Gamma-Ray Space Telescope, the Laser Interferometer Gravitational Wave Observatory, LIGO, and the IceCube Neutrino Observatory provide glimpses into high-energy astrophysical phenomena that might signal hidden dangers. Yet, the sheer scale and subtlety of these threats mean that some will inevitably go unnoticed until catastrophe occurs. The universe's silent killers are a reminder of the fragile thread on which life and matter hang. They challenge our sense of cosmic safety and highlight the importance of vigilance, scientific curiosity, and humility in the face of an indifferent universe. In contemplating the hypermagnetar and other silent killers, we recognize the paradox of existence. Amid the star's breathtaking beauty and mystery lies an ever-present potential for sudden, invisible destruction. These hidden cosmic predators do not discriminate. They do not pause or hesitate. They are the ultimate arbiters of survival and extinction, their power measured not in light or sound but in the quiet unraveling of reality itself. This haunting truth compels us to look deeper, to search farther, and to prepare as best we can. In doing so, we not only safeguard ourselves but also honor the fragile miracle of life that exists against such cosmic odds. In the vast, silent void of space, far beyond the reach of any human eye or telescope, there exists a star unlike any other, a cosmic monster cloaked in darkness, a ghostly predator lurking in the shadows between the galaxies. This is the hypermagnetar, a star so deadly, so unfathomably powerful, that it does not need to consume worlds with fiery destruction or gravitational collapse. Instead, it erases them, atom by atom, molecule by molecule, with a magnetic force so strong it tears the very fabric of matter apart across unimaginable distances. Imagine this star alone, suspended in the abyss, its surface an inferno of crushed matter and unimaginable energy. Unlike the fiery blaze of our sun, the hypermagnetar's light is dim, almost invisible, swallowed by the cold emptiness that surrounds it. No planets orbit this star, no life thrives here. Instead, around it stretches an invisible sphere, a silent death zone, that extends across light years, an area where atoms unravel, where molecules dissolve, where chemistry itself is shattered by the relentless assault of magnetic fury. Picture a drifting spaceship, or a planet wandering too close. They do not see this star coming. There is no warning flare, no brightening beacon in the night sky. Instead, the magnetic field creeps forward, an unseen force creeping silently, ripping electrons from nuclei, destabilizing matter, distorting space around them. The very building blocks of reality begin to fray and tear as the star's influence envelopes the doomed object. No alarms sound. No cries echo. Only the quiet, inevitable disintegration of everything that dares to enter its radius. The star's power does not diminish with time. It spins rapidly, fueled by the remnants of a hypernova explosion, its magnetic field amplified to godlike proportions. Gravity and magnetism intertwine here, creating a deadly dance that warps space and shreds matter in equal measure. Even light itself bends and twists in this dark domain, distorted by magnetic fields that make photons split and recombine in strange, unsettling ways. The star's heartbeat pulses in gamma rays, bursts of radiation that sweeps silently across the galaxy, scorching distant worlds in their path, extinguishing life before it even knows what hit it. This is no star of warmth and life. It is a cosmic executioner, a predator that kills not by chase or collision but by presence, by sheer, unrelenting force. Like a black hole, it is a final destination, but unlike a black hole, it does not trap matter behind an event horizon. Instead, it dismantles matter from the outside, from afar, turning solid ground into drifting clouds of ionized gas, stripping atmospheres from planets, scrambling the electronics of spaceships, and leaving nothing but void where once vibrant systems existed. And yet, the hypermagnetar remains hidden. It waits in the darkness, cloaked by the very forces it wields. Invisible to the naked eye, invisible to most instruments, it is a silent enigma, a secret killer lurking in the cosmic shadows. It embodies the terrifying truth that the universe is not only a place of wonder but also of danger, where forces beyond human comprehension hold the power to unmake worlds with the quiet flick of magnetic fields. For any civilization in the galaxy, the arrival of such a star would be a sentence without trial. No matter how advanced or prepared, no warning or defense could stand against a threat that unravels the atomic bonds of matter itself. The hypermagnetar is the ultimate predator, patient, merciless, and absolute. As we gaze up at the night sky, bathed in the light of billions of stars, it is chilling to consider that among those points of light, or in the unseen darkness beyond them, there might be a star like this. A star that waits, silently and eternally, to erase everything that drifts too close. This haunting image, a lone star in the cold vastness, an invisible sphere of annihilation, should leave us uneasy. It reminds us that the cosmos is not just a stage for creation but also for destruction of the most profound and mysterious kinds. It challenges our understanding, sparks our curiosity, and warns us of dangers lurking beyond sight. In contemplating the hypermagnetar, we confront the universe's ultimate paradox: beauty and terror intertwined, creation and destruction woven into the same cosmic fabric. It is a star that ends worlds, a silent killer beyond measure, a grim reminder of the fragile, fleeting nature of existence amid the infinite vastness. And yet, despite the unease it inspires, this star captivates the imagination. It pushes the boundaries of what we know and invites us to look deeper into the mysteries of the universe. To seek, to learn, and to prepare for the wonders and dangers that await us in the dark. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.